think someone is texting. Can we check?
Do you have audios for this? Oh, yes, yes.
Okay. Awesome, thank you. Okay, so where was I? So what I was saying is that the world is compositional, which means that the parts should not be seen in isolation. On the contrary, objects should be seen as collection of parts, and 3D scenes should also be seen as collection of scenes. And as you can imagine, there is not only a single flat representation. We can consider relationships between parts such as symmetry, proximity, etc. And for the case of scenes, the possibilities that we have in terms of the possible the possible relationships that can be captured are even more immense. Compositional learning has been extensively used for many tasks, for many 3D perception tasks, such as 3D reconstruction or manipulation, as well as a lot of robotics application. And the reason for this is that compositional representations can be particularly useful if we want to have a representation that better captures the semantic abstractions of objects and scenes. What currently might be more exciting about is compositional representations for generative tasks. So we have seen compositional representations being used for generative tasks of scenes, objects, and in a couple, I'm very confident that we will also very soon see representations for more higher level and more semantic concepts such as interactions, etc. Okay, so what are the topics that we will try to cover today in the workshop? So first of all, we will, I'm sorry for this, we will try to cover what are the best structural and compositional representation for different types of 3D data, such as depending on if you have point clouds or if you have voxel grids, etc. Of course, this is a very difficult question to answer, and I don't think that anybody can do this reliably. In addition to that, I think a very interesting question to ask is what is the best structure that we can use? The answer here is a bit dependent on the type of the underlying relationship between parts or objects that we want to capture. We will see throughout all the talks of today's workshop, people from different fields, and hopefully we will be able to understand how this type of data are used in applications such as robotics, a bit more pure perception, as well as some generative tasks. And we're very lucky because we have a great set of speakers today. We have 4 amazing keynote speakers, as well as 6 great spotlight speakers. So in this workshop, we'll encourage and always try to find people from that are both senior as well as less senior, because we hope the spotlight speakers will provide a bit more hands-on experience, share a lot from their struggles when they were trying to, solve their bug, etc. Whereas keynote speakers will offer us their vision, and we will be able to better understand where they see the field going. In addition to that, we have 11 presentations, paper presentations, and there will also be a poster session later on. And that session was supposed to end at 8. We are already horribly late, but that's okay. And let's start with the first keynote presentation, which is from Hin Tong. I pronounced probably the name completely. Yes.
Yeah, I think correct. Yeah, thanks.
So let me see if I can do the presentation. So while this is downloading, I can say a few words for him. So Hin Tong is a partner research manager at Microsoft Research Asia, where he leads the Internet Graphics Group. His research focuses on computer graphics and 3D computer vision and covers many topics, including appearance modeling and rendering, texture synthesis, light transport capturing and analysis, image-based modeling and rendering, as well as 3D learning, facial performance capturing and animation, and 3D graphics systems. He received his PhD in computer graphics from Tsinghua University in 1999, And he regularly serves as paper committee members and area chairs for both graphics and computer vision conferences. He's an associate editor-in-chief of IEEE TV CG and an associate editor of IEEE CG and A. And he has been an associate editor of ACM TOG, IEEE TV CG, and Computer Graphics Forum. So we need 1 more minute for his presentation to be downloaded. And I just want to encourage you to ask questions. So you can post your questions either via Zoom or put it like on the chat. And there will also be, for the poster presentations, you will have the chance to ask all the speakers during the poster session. We will try to have some time for questions during the keynote and the spotlight presentation. Give me 45 more seconds and we can start. I think everybody is.
Could you try go to the participant and see if you can make the other CVPR workshop co-host or something? So we don't have to. Hopefully I don't break anything. There's 2 CVPR workshops. Make host. Oh, we can only change hosts. So you can only be the you need to be the host to. Do you need to be the host to? We can try, but I don't want to break things.
Okay, so let me play the video. So I just want to say that Hink is on Zoom, and afterwards he will be able to answer any questions. So let me start. Let me know if you cannot hear the audio. Do you hear anything? No, right? Hink, can you hear me? Does your presentation have a video? Audio.
It seems that I'm not sure. It seems that you need to set up to make the desktop audio or the audio from computer can be delivered to Zoom. So I'm not sure if still not okay. Maybe I can share my screen and present there lively.
Can someone on Zoom say something just to?
Sometimes the audio comes like that.
So, okay. You see, there are 3 outputs here. I don't know what else.
See, screen share. Oh, is the screen share?
No.
Let's share screen first. We're sharing this, right?
Oh, session.
Share sound, yeah, share sound, and that should work.
Yes, can you hear it?
This is the thing,
Okay, yeah.
right? All right,
Let's
let's
see.
see if it works now.
Modeling and learning 3D structures. I'm sorry that I cannot be on site to give this talk. Many organic objects or man-made shapes in the real world, such as human bodies
I
and
think we need to
faces,
ask
as
some
well as the
comment.
chairs or airplanes shown here,
Shouldn't we have
always
like
have
a-
very similar structures. So learning these 3D shape structures is an essential
There was a message on chat.
Okay, so people on Zoom can hear the audio, but we cannot hear the audio.
Okay.
That's hard.
Okay, good. That's a good feedback.
All right.
But we also need to hear the audio, right? So settings. Sound.
task for many graphics
I
and
think we
vision
have to do it
applications.
through here.
In shape completion and reconstruction, structure acts as a prior to map incomplete noise observations to complete 3D shapes. In 3D analysis and understanding, the
Okay.
3D
Okay, I think now we can also hear the people.
The people on Zoom confirm that the audio is still audible? Okay, cool.
Okay,
Okay.
awesome. Let me play the video. Sorry for the struggles. Okay.
Good morning, everyone. And in this talk, I'm going to talk about our recent work on modeling and learning 3D structures. I'm sorry that I cannot be on site to give this talk. Many organic objects or man-made shapes in the real world, such as human bodies and faces, as well as the chairs or airplanes shown here, always have very similar structures. So learning these 3D shape structures is an essential task for many graphics and vision applications. In shape completion and reconstruction, the learned shape structure acts as a prior to map incomplete noise observations to complete 3D shapes. In 3D analysis and understanding shown in the middle, the 3D shape structures provide robust features that are independent to the shape details. For geometry modeling, the shape structure provides an efficient way for users to generate and edit 3D shapes. However, learning structure of 3D shape is also a very challenging task. For 3D shapes in one category, they also have their diverse structures, and the space of all shape structures is discrete but not continuous, which is difficult to be learned. Moreover, labeling structure of 3D shapes is a labor-intensive process, which makes the amount of the labeled data for training is quite limited. In the past years, researchers in vision and graphics fields have taken great efforts to enlarge the labeled dataset, develop a supervised method and unsupervised method for modeling and learning 3D structures, which greatly advanced this field. In the past several years, we also did some explorations on modeling and learning 3D shape structures and applied the learned 3D structure in different vision and graphics tasks. So in the following part of this talk, I will present 4 works along these directions. So in these works, we try to answer 2 questions: how to represent the shape structures and how to learn it efficiently from the labeled or unlabeled dataset. The first work I will introduce here is try to learn an explicit 3D structure representation from the labeled dataset and then apply it for 3D reconstruction. The work has been published in CVPR 2019. As shown here, the goal of this work is to develop an efficient method for reconstructing 3D shapes with complex topology structures, especially those shapes with thin structures. Our key observation is that the skeleton provides a good representation of the shape topology and structure. As shown here, a skeleton of the 3D shape is composed of curves and sheets. It can be extracted from 3D shapes by shrinking the surface along the reverse directions of the surface normals. As a result, The skeleton will ignore all shape details and only represent the topology structure of a 3D shape. Based on these key observations, we present a hybrid hierarchical representation for 3D shapes. In particular, as shown here, we model a 3D shape with skeleton for shape topology, discrete 3D volume for all shapes, and a continuous 3D mesh for surface details. Based on this representation, we developed a learning scheme to learn 3 cascaded encoder-decoder networks for reconstructing 3D shape from single-view input image. Here we show the single-view 3D reconstruction results generated by our method and other methods. Note that our method can well reconstruct the scene structure of 3D shapes from single-view input image. Numerically, our method also outperforms most of the existing methods at that time. Here we show some 3D shapes reconstructed from the real images. Finally, our ablation study validates that the learned skeleton representation is critical to reconstruct the scene structures of the 3D shapes. The first work describes how to learn the shape structure for 3D reconstruction. In the second work, we try to learn the shape structure and use it for 3D generation. To this end, we develop a generative model for high-quality 3D shape generation. We want our method not only can be controlled by the users for generated shapes with desired local structures, but also can be generalized to other shape categories that are not in the training dataset. This work will be presented in this year's SIGGRAPH. The key idea of our method is to train a diffusion-based 3D generator that can be controlled by 2D sketches. Our key observation here is that the 2D sketch provides good prior of the 3D shape structures. It can be easily drawn by the user or extracted from a real 2D image, while the 3D diffusion model can be well reproduce all 3D shape details learned from the training dataset. Based on this key idea, we developed a 2-stage diffusion model for high-quality 3D shape generation. In the first stage, our occupancy diffusion model learns to generate a low-resolution occupancy field of the 3D shapes. Then in the second stage, our SDF diffusion model refines the generated occupancy field with a detailed sign-disease functions. We also develop a view-aware local attention scheme to control the shape generation by projecting the input sketch to the generated shape volume so that the user can efficiently control the local shape structures via the input sketch. Please see our paper for more details. Here we illustrate the 3D shapes generated by our approach. You can see that compared to existing sketch-based 3D modeling methods, our generative method can generate higher quality results that follow the shape structures specified by the input sketches. Also, as shown on the left, our method can also generate reasonable 3D shapes from the 2D sketch input for unseen shape categories. On the right, we demonstrate that our method is robust to hand-drawn sketches. We just discussed 2 works that learn the shape structures from the labeled data for 3D reconstruction and generation. In the third work, I will introduce how to learn shape structures from unlabeled shape collections. The goal of this work is to learn the shape structure of 3D shapes in a class by shared qubit shape abstractions. We hope this shape abstraction is consistent for shapes with the same structures and can well handle structure variations of the different shapes. For example, if a chair has no arm, we hope that the boxes for the arms are not in its shape abstraction results. Also, we want to learn it from the unlabeled shape collections. So, how we can present the shape abstractions that can meet all its requirements? We have two key observations. While 3D objects in a class have various structures, they share a common structure at a higher abstraction level. For example, the three airplanes here have different structure details, but they are all composed of one single airframe, one tail, and two wings. Secondly, different shapes may exhibit different structure details in different abstraction levels. For example, the tail for airplane has a more fine-grained structure than the airframe. Based on these two observations, our solution is an adaptive hierarchical qubit representation. On the left is the input 3D shape. In the middle is the hierarchical structure of the abstraction. And on the right is the adaptive hierarchical qubit representations. We want to capture as much as possible structure details on multiple levels and get a coherence abstraction at a higher level. Given this hierarchical adaptive qubit representation as target, we need to learn a network to construct its representation from unlabeled shape dataset. To this end, we need to tackle several challenges for a given 3D shape. How many qubits should we use? And what hierarchy should this abstraction follow? Finally, how to optimize the parameters of the qubit? To this end, our solution is to learn a multiple-level qubit representation with redundant number of qubits in each level. Then we learn another tree selection network to get an adaptive hierarchical qubit for each input shape. We use the shape approximation error to regress the box parameters. So as shown here, our solution is an unsupervised learning method. It consists of three components. Given an input 3D shape, we use a shape encoder network to get a latent code. Then, the qubit prediction module decodes the latent code to three levels of the qubit abstraction with a hierarchy structure. Next, the qubit selection module predicts three levels of selection masks represented by binary signals. Using selection masks, a set of qubits are picked from the hierarchy to form the adaptive qubit abstraction. During training, we update the qubit prediction and selection module iteratively to refine the masks and the qubit parameters. And finally, we get a good adaptive qubit abstraction of the input shapes. To train this network, we also design a set of loss functions for each branch. Please see our paper for more details. Here are the abstraction results predicted by our network. In each category, the qubit with the same color are correspondence part in different shapes. The body of the airplane is represented by the blue qubit, and the seat of the chair is represented by the red qubit. We compare our results with the previous work, which is also a unsupervised learning method for qubit abstraction. They use a single-level qubit setting. Without any hierarchy, their method cannot well address structure variations and result in oversimplified abstraction. Here we show structure-based classification results. We cluster all the chairs shown here by their abstraction structures. In the same group, all the chairs have the same structure, while different groups have different structures. Also, the blue cubit represents the chair back, and the red cubit stands for the chair seat. In all three works discussed above, we model the shape structure in an implicit way. In the last work, we try to explore whether we can model the shape structure in an implicit way and learn it from the unlabeled data. The answer actually is yes. Our key observation is that the structure of 3D shapes can be modeled by the part correspondence between the 3D shapes. So if we have dense correspondence between the 3D shapes, the structure actually can be easily identified from one or few examples. For example, for the sofa and the chair shown here, their shared structures such as the legs and back can be easily identified by the point correspondence shown here, while the structure difference of the two shapes can also be identified by the missing correspondence of the points on the sofa arms. So based on this observation, the goal of this work is to learn a representation of the 3D shapes in one class and their dense correspondence. We hope the learned shapes representation can faithfully model the 3D shapes in one category, and the point-to-point dense correspondence can well handle structure variations. Moreover, we hope the representation can be learned from the unlabeled 3D shape collections. Our key idea is to model the signed distance field of a 3D shape as a deformation of a template field shared by all the shapes and then correct it with a residual field. Here we illustrate our representation with a 2D slide of a 3D chair. Note that the template field shared by all the shapes actually encode all the possible shape structures in the shape collections. The deformation field then models the correspondence between the 3D shape to the template. The correction field actually corrects the deformed template and filter off all structures not in the current shape to get the final shape details and structures. We model the deformation and correction field with one MLP and the template field with another MLP. A HyperNet MLP is learned to infer the parameters of the deformation field for each 3D shape. The three networks are trained from unlabeled 3D data with reconstruction laws and another constraints. Please refer to our paper for more details. Our method faithfully encodes all the 3D shapes and outperforms other deep shape representations, as shown here. Also, based on the dense point correspondence, our method can easily generate shape structures by transferring the point labels from sparse examples to each 3D shapes. Here we demonstrate that our method is better than other deep learning-based shape correspondence methods and can generate better shape segmentation results. Here we show the texture transfer result. You can see that the learned point-to-point dense correspondence between the shapes follow the shape structures and well handle structure variations of the different shapes. For example, you can see that the texture on the arms of the first chair is not transferred to the other parts of the chairs without the arms there, shown on the second. Finally, our learned repetitions also enable efficient shape editing, as shown here. After the user edits one point on a 3D shape, our method changes the shape to fit the moved point and keeps the basic structure of 3D shape unchanged. To the best of our knowledge, it seems that there are still no other method can do the same editing operations and still keep these rigid or non-rigid shapes structures of the original shape category. I think the four works I presented above have convinced you that the 3D structure is valuable for both 3D reconstruction and 3D generation and many other tasks. However, I think you will also agree that the 3D structure learning is still a challenging task. For different tasks we shown here, we actually carefully designed different repetitions for modeling shape structures and developed different networks and training schemes for learning shape structures from either labeled or unlabeled dataset. Still, there is no unified solution that we can use for all these tasks. Looking forward, we are exploring several things on 3D structure learning. It is unclear whether we can find a unified representation for 3D shape structures and efficient learning schemes that can disentangle the 3D structure from 3D shape details. Also, we are seeking for self-supervised learning methods and networks that can provide a unified framework for both 3D structure understanding and generations. Finally, it is still unclear how to extend 3D structure learning from one shape category we have done here now to all 3D shapes in the wild. And probably the learning from text, image, and video data will provide helpful solutions here. We believe that these challenges are also big opportunities for 3D learning and generation. Finally, we have released our code and data for all the projects presented in this talk. I would also like to thank my colleagues, interns, and our external collaborators for their contributions to the projects presented in this talk. And that's my talk, and thank you for your attention. Good morning, everyone. And in this talk, I'm going to talk about.
Thanks a lot. This was a great talk. Sorry for all the technical challenges that we had. Are you still with us, Kim? I think they can, but we don't hear them again. Okay. Can people on Zoom say something, please?
Hello? Can you hear me?
I can hear. Okay. But if you say something, I don't think we can hear you. Yeah. Can you try to say something?
Hello, hello.
Hello?
I think the problem is that we don't hear the sound from the Zoom. Audio sound.
Us? Are we audible on Zoom?
Yeah, I can hear you, Despi. Can you hear me?
I can hear you.
Okay. Can someone on Zoom try to say something, please?
Hello, test. Hello.
Not hearing. I don't know what's going on. Can we ask someone to come? Can someone on Zoom say something?
Hello, hello. Can you hear me now?
Good, great. Okay. Are
Great.
there any
Yes.
questions from the audience to him who is with us on Zoom? Yes. Can you please try to come to the microphone and ask your question?
I think this is Jianfei from Monash. Okay, so I have two questions for you. Thanks for the talk. So my first question is, in your third work, you talk about this kind of shape parsing or shape abstraction work. So I'm wondering, like, I mean, what kind of additional application you have in mind? Say, in addition to parsing this kind of shape, do you think about like it can be used for like shape generation? So this is my first question. And then my second question is, in your second work, you talk about this kind of diffusion for 3D. So it seems you change, I mean, between the different 3D formats that are there. So for your first UNet, you use kind of occupancy kind of representation. And then you kind of switch to mesh, right? In order to use this kind of subdivision. And then after you use mesh, then for your second diffusion model, you use you kind of use this kind of SDF representation. So can you share with us, I mean, what's the insights there? I mean, why do you want to sort of, I mean, switch between the different formats? Thank you.
Thanks, Jianfei. Yeah. So I think that there are two good questions. Yeah, great questions. Thank you. So for the first one, yeah, I agree with you. Yeah, I think the shape abstraction will provide, in some sense, consistent, some qubit representations for all the shapes in one categories, and let me say. I think it's possible for us to use this representation and apply it for shape generation. But on the other hand, we didn't keep exploring along this direction just because we found that finally to obtain the good shape abstractions there, we really need to design a lot of different loss functions and to balance different regularizations to achieve the good result. And in some sense, we meet some difficulty to generalize the approach for different kind of or different shape categories there, in some sense. That's our difficulty. And so we are switched to exploring other possible solutions there. Yeah. But definitely, I think it's possible to say whether the abstract shapes can be used to give you some structural representations and then use for shape generation. For the second question, and I'm sorry that I didn't explain it clearly. So after we obtain the occupancy field, so the subdivision is that we simply increase the resolution of the voxel resolutions there. And after that, we in the higher resolution volumes, we do the diffusion models for the SDF and obtain the shape details. And we separate it as a two steps just because we found that if you use a single step, it's so difficult to balance what kind of OO shapes or shape details you should be generated. I think somehow it's quite similar to when the people do the 2D diffusion models, they also use the multi-scale approach to first generate all 2D image at a lower resolution. Then you have another diffusion model to increase resolution to do the super resolution works. I think we share the similar ideas. Yeah, there. I'm not sure whether I answer your questions there. Yeah, thanks.
If people have more questions, we can have one more.
Thanks for the great talk and presenting such interesting papers. I had a question on your last paper. So from my understanding, you get this dead shape correspondence by through sampling common points on the template shape. I was wondering if you had to do any special kind of regularization to prevent mismatched correspondences during your training.
Sorry, you mean the yeah. Sorry, let me repeat your question to make sure that I hear it clearly. So your question is that whether I use any regularization to avoid the mismatched correspondence in the training process, right?
Yeah, because I guess just to clarify, for example, if the deformation field that you learn sort of takes points from the template to different parts of different shapes that you generate, you have a mismatch correspondence. So I was wondering what you do to prevent that kind of mismatch.
Yeah. Let me say this. Yeah, good questions. In our current implementation, we use this normal consistency constraints, and we found that will help us to give us a better correct correspondence between the different shapes. For example, if we have a car or a chair there, that will avoid some, for example, for the chair, that will avoid some point on the chair back will map to the chair base on another chairs. Yeah, we found that that be very useful. But I think the key idea here is that we found that to build this shape correspondence between the two 3D shape or two 3D surface, 2D surface there, we actually need to have this correspondence in the whole volume, which means the 3D to 3D correspondence. That help us to avoid a lot of errors or mismatches if you try to build the 2D shape, 2D surface to 2D surface correspondence, just because definitely you will make some mistakes for the missing structures or mismatched parts. Yeah, like some part is missing on the other shapes here. So 3D volume correspondence, by default, you can get the identifier mapping, right, to the same position there. And from that, when you have the more template and deformation field there, always we find that a smooth deformation field will give you a good results. Yeah. Not sure whether that helps to answer the questions here.
Okay, thank you very much. That was a great talk. If you have any other questions, maybe directly post them on Zoom because we are running really late. So
Sure.
I would like to invite our next speaker, Andrea Tagliasacchi, to join the podium because I think we will need some time to set up everything here. Yes. From this one? Okay, so maybe I can do it.
Can people on Zoom still hear us?
Yes, but the volume is a bit low.
You can text it to me on chat. What? No, not the password, the Zoom code.
Oh, I'm sorry.
Probably, yeah.
Okay, let me see if it will.
Is it on the workshop
Yes, if you can do it.
page?
Okay, so you said the audio is a bit low, right?
Okay, so
And if you go to the virtual CVPRs, maybe
I've never asked like if people are hearing on us on Zoom do this for like this.
Yes, I'm in big.
let me send it.
Let me see. You can send it.
Can I unplug you? Connect my oh, you want me to present through Zoom? Okay.
Yeah,
All right.
because
Yeah, just share the screen.
Yeah,
it's Slack or Hangout.
Hangout. I didn't know you were going Zoom. I was ready to just plug in and go. The joys of hybrid conferences, right?
Unplug and plug everything.
Yeah, I don't know. I hear you. Yeah. Don't do it. Yeah.
Can you hear me?
Yes, yes.
Okay.
Yeah, I can hear you.
Let me try this just to see if it is better. So is the sound now better or is it worse?
I think it's roughly the same. Yeah, I can hear you, but it's just the voice is low.
I never had a problem with it from my laptop.
Okay, then
So
I
I can
mute.
mute these and
I'm
then.
not sure if this does it properly because you have to do a bunch of. I mean, we can do it. Maybe you can
I can do the intro.
Yeah, the voice is getting bigger. Yeah. Hi.
I turn on.
Oh,
Hello? Nope. There is two microphones on.
I think you should close your sound.
I'm a Google boy, remember? Yeah, maybe. So this is the out, but still the video looks horrible. You think the problem is on my side? You're the expert. I have no idea how to do Zoom, so it's like. Oh. I don't know if CVPR has enough bandwidth for me to. Yeah, you need the. You can just give me USB-C and I present live, and
we should just do the.
and then I just broadcast to the so the offline people will get a. Yeah. I don't think.
You need
Yeah, I enabled it. So that was the. That was the funny bit.
maybe
Yeah.
you can stop sharing.
Yeah, maybe that will work.
Stop sharing. Okay.
Sorry.
You tell me what to do. As I said, it's like I have no idea.
How to use this?
What? So this is from the USB-C.
Yeah, but how do people on Zoom see this?
You have to join and then see.
Cool.
Let's see.
Yeah. Yep, we have the. Oh.
I mean, this will work. I use this all the time. You have to mute yourself, so.
Okay.
Yeah.
Can people on Zoom hear us?
Yes, yes, pretty
And the
clear.
quality of the video is audible, right?
I think it's fine on this.
It's fine now.
Here is fine, but this because you're getting my laptop
Yes.
feed, but online
So
it's like 5 pixel wide.
Kaitsun, on Zoom, how is the video quality?
I'm not seeing any video. I can see the full slide sharing, like
But
for the
is it
first
good?
slide.
Do you
Yeah.
see, or is it pixelated?
No, no, the screen looks good.
All right.
Give us 1 second to introduce.
Sure. How much time do I have though, considering the video is
What do you-
30?
We,
All right.
we can.
Okay.
Yeah, let me just do a very quick introduction for Andrea, who is our second speaker and an associate professor at Salmon Face University. And he also holds a part-time staff research center at Electrical Brains Toronto. His research interests focus on 3D visual perception, which lies at the intersection of CD, computer graphics, and machine learning.
Great. Thank you for the introduction. I'm excited to be here. I'm also a horrible person to give this talk because I'm going to try to convince you that explicit part-based representations are not going to be the way forward. And that Zoom decided to share the audio, which is really not good. Okay. Okay, so just to give you a bit of background. So before I moved to deep learning, I was working a lot on power-based representations, right? So these are for like computational reasons, to make it fast, to make it flexible, to make it controllable, give artists to tools, and perhaps even control robotics. And as we moved into deep learning, we tried to bring some of those tools from the graphics community into the vision community, right? So we had, for example, BSPNet that was trying to represent a complex piece of geometry via collections of shapes. NASA that was trying to do a part-based representation of humans with neural fields. Canonical capsules that try to do unsupervised learning for point clouds using the composition in parts. And then recently, there's been a more recent thread of mine working more like neural fields, kind of like across the spectrum of applications, right? Some of them part-based, some not. And this is just an highlight of what will be at CVPR this week. So if you find this talk interesting, maybe you can drop by and say hi to the students that work so hard to work on these topics. And here, as you can see, it's like there is a trend, right? So basically, almost everything I'm doing these days is based on fields, right? Continuous representation throughout. Perhaps at the very, very end of the application, you perform a discretization step to go from a continuous representation to a discrete representation, right? But if you then contrast this to what I was doing a few years earlier, like the first 3 papers up top, on the other hand, those have a discrete representation more natively embedded within the reasoning modules, right? Okay. And so what basically I'm saying is that right now I've converted myself to be a fully continuous throughout, never go discrete kind of person. Yeah. And so you can see it's like we apply this to a number of different applications, from camera calibration to localization in maps, super solutions, and NERF is all the rage, but yeah, whatever. So just to give you an idea, so let's try to contextualize the talk within the hot topic of NERF. So if you're not familiar, yeah, it's now, as of this year, is the hottest topic at CVPR, right? Since more classification labels. But the idea of NERF is to start from a collection of calibrated images, and then via optimization, build a representation of the scene. Could be neural, could be not in more recent instances. But the question you should ask yourself is, how is this process taking place, right? So what is controlling the model and the quality of the result that you get on the output side, right? And so if you look at the internals of NERF, you have actually essentially a neural network or a grid or combinations thereof that gives a mapping in between a position in space and some quantities that are used for volume rendering, right? So to convert knowledge stored in a volume to knowledge that you will observe from an image. And then this entire workload is just trained by comparing the color predicted by the model along a particular array to the color of the pixel in a particular image, right? So you just sample an image, sample a pixel, and make sure that the model and the image are saying the same thing. And this entire thing is controlled by classical volume rendering, right? So nothing overly complicated. But now, if you think about NeRF optimization as an optimization problem, a lot of people have actually forgotten what happened before deep learning, right? So, and I claim actually that this is actually what happening, right? So you want to find, in a general inference problem, you want to find the connection or the likelihood that connects your data to your model, right? And so you want to find some distribution that maximizes the joint likelihood of the two, right? So you want your data to explain your model and vice versa, okay? And with bias rule and a bit of reshuffling, you obtain the expression that you have in the second line right here, okay? And so if you now think about it, you can now recast NeRF optimization, or in general, these like image-based driven 3D reasoning pipelines as a maximum likelihood and a maximum posteriori model, okay? Where you have a likelihood term that is nothing else than the optimization of photometric loss, right? This is the one that we saw a couple of seconds ago. But then if you admit that that is the case, then you should ask yourself, is that NeRF doing any map, right? So is there any prior inserted in the optimization? And if there is a prior, what is that prior, okay? So the first one is that there is the inductive bias of volume rendering. So you get, light travels along straight lines and integrates through volume, okay, fine. But then there is another prior that is implied by the networks that all of these models have been using, right? And this is actually the spectral bias of MLP. And so you can say that the classical version of NeRF, or the first version of NeRF, and this is still true for many models, is nothing else than a map model where your likelihood term is just your photometric reconstruction and your prior is just like, please use smooth functions when doing so, right? And most of NeRFs are trained as optimization. Even the one that generalize, they're running an optimization for a new scene every time you feed in a beating batch, right? So it's just the same over and over. And so the question is like, I want to give a little bit of a historical perspective on how map-like problems are inserted within reasoning pipeline, right? So you can say, well, now all these problems have a connection in between your model and your data, which is your likelihood term, and a prior, okay? And over the last, it depends if you linearize the growth of papers, it will be centuries ago, but over the last 2 or 3 years, okay, we have actually seen a transition of how we embed priors and likelihood terms within deep learning models. And so I'm going to give you an historical perspective from how I've been working on it and also how it connects to like compositional learning, right? So the first one is, we're going to start from here, from this encoder-decoder architecture from CVPR 2020. So this is ConvexNet. And the idea, many papers at the time had an architecture that looked like this, right? So you want to do extraction of 3D content from a single image. So you feed your image through some encoder that produces a representation for that image. And then you have some decoder that digests that encoded representation and spits out something that you can either render or supervise, okay? Back then, we didn't have differentiable rendering figured out quite yet. And so what we used is that we used ground truth 3D data, right? So we had a mapping in between a rendered image and the 3D model of that image. And then we will try to learn an encoder-decoder that will preserve this mapping, okay? And back then, the structure, like the composition problem was, well, you can do it with implicit functions, but on the other hand, we want something that you can take and plug it into a game engine directly, right? So that your vision pipeline and your like data exploitation pipelines are more closely connected without any need for conversion. And so that was a pretty interesting bit, and essentially it amounted to, the encoder is simple, it's a CNN. Here you can put a VAE, or sometimes that's not even needed. And then on the decoder side is how do you design this decoder right here? And back then, in a compositional way, what we did is that we extended this work IMNet that really was inspiring. I mean, like that result on the top right really like kind of like changed my way of thinking about 3D deep learning, actually. So this work, Jishin is actually sitting right here. He had the first paper on neural fields in 3D vision, according to archives timestamping. And it really changes my way of thinking. Like if you compare how you treat these encoder-decoder architectures, and you just see how a CNN decoder would do with respect to a neural field, you look at the result and it's like, what's going on here? It's like, that's so much strikingly better that there must be something very interesting happening underbelly. And zoom 4 years forward, and now like the vast majority of 3D vision is actually using neural fields to operate. So, and the way in which it was done, it was extending these neural fields model, right, from just having a single feature vector that produces a single shape in output to connect them more to a compositional learning kind of like structure. And so what we did is that we said, well, we're not going to only spit out a single latent code to control the shape globally. We're going to spit out a collection of latent codes. And this set is of it's a bounded cardinality, okay, just fixed cardinality. And then we're going to spit out the location of each of these components, right? So basically, each of these latent codes beta will encode up to a fixed decoder the shape of this chunk of geometry. The transformation T will tell you where to put it in space. And then you can combine the entire thing by a spatial max operation to obtain your full shape like that, okay? And again, the core is how do you write this function C right here. I'm not going to go in details, but it turns out that if you want a polygonal representation, you can actually convert a convex set of constraints, so this is a set of half-space constraints, into an occupancy function, right? Which is what a lot of paper, or an SDF actually, both of them work. And that's just the algebraic expression that gives you differentiable, basically, hyperplanes within the optimization. And here you can actually build a nice generative modeling, right? So this space actually encodes relational characteristics in between parts, right? In a way that is connected. So the, I don't know, for example, on airplanes, the third part will always be the tip of the airplane, right? But then it allows you a way of doing learning across shape categories in a part-based like representation, which was, I think, was pretty interesting at the time. And so the question right here becomes, what is this prior model right here, okay? So the prior model in this case was the fact that you have a collection of K parts, ordered, right? And then these K parts can slightly morph in space to fit a particular piece of geometry. And the inductive bias of this is very similar to the one to nerf, right? The only thing that says that you have to chase, maybe I should stop this video, but you can see that one of these parts only moves a little bit, okay? And it deforms a little bit. It doesn't deform drastically as you navigate the latent space, right? And so the inductive bias that you have in this prior right here is again the same of the one on nerf. You just basically asked for your problem to be explained with smooth functions. Okay? So very similar. Now, if you zoom a little bit in the future, this path dried up a little bit, right? This a way of having a global encoder that just spits out a geometric model supervised by 3D data. It kind of died off because now we know how to supervise on this side using images, right? That's where nerf came in, because it gave us a better encoder to connect image data to my internal representation. Oops. And the other thing that happened, on the other hand, was that when nerf came out, there was this idea or this concept of positional encoding, right? And when, as soon as I saw this result, the afternoon, I went to Boyang and I said, please, add positional encoding to our decoder for this guy, and let's see if the quality of the mesh that you gets from these smooth blobby things, which are good for many robotics applications, to something much sharper. And absolutely nothing happened. And so we were a bit puzzled, right? What on earth is happening? When you're in the overfitting setting, it works so well for nerf, but then when you go into this encoder-decoder setting, you cannot apply the same posent encoder data to this term, and just nothing happens, right? And that puzzled me. This is going to kill me sooner or later. It's like some yellow bands. And all right, so that was puzzling, right? And this is basically what killed this way, for me at least, this way of approaching the problem. And really the issue is this with encoder-decoder structure, right? Unless you do something else like projected feature from images, this creates an informational bottleneck. There is not enough representation power that is flowing from encoder to decoder. It's a bottleneck. It's a giant bottleneck. And so this actually leads me to the next part, right? So we went from these encoder-decoder representations, and then the next chunk of my life was spent in autodecoder settings, which on the other hand can preserve a lot more of the data, right? So the perspective you should have is like, why, okay? Why, when you were doing part-based representation, even if you made the parts molds, everything would just move, but then you move to an autodecoder setting, and everything can actually be very highly detailed. And so the problem statement that we had in this particular project was to kind of flip nerf on his belly. So nerf will be, the classical nerf will be here on the left, many images of one scene. And on the other hand, we care about the complement space, right? We have many scenes, but of each scene, we have a single image. Okay? And so we're trying to build a latent space to control our optimization. And if you go back to our losses from earlier, the only trick is basically that you add a conditioning term to your neural field model, right? So you just had one of these latent code Z right here, and now rather than rendering one scene, this code Z will be associated to each of the scenes that you want to render. Okay, they're not very large to store. You can keep them in memory actually. And then you build a conditional nerve model that also takes this code Z in input, not just the position of array. And you get something that looks like deep STF, for example, from an autorecorder point of view. And you do something to avoid mode collapse. You give camera hints a little bit. But again, if you open this model, one of the key things that we did back then that made kind of like everything work is actually, again, putting a prior, right? So again, maxima posteriori is that you cannot just rely on just like feeding your data and calling it a day. We actually had to add priors. And the priors in this particular paper, can I remove that band up top somehow? Hide floating meeting control, this one? Oh, okay, thank God. Okay. God, Zoom. Okay. Yes. Yes. It's because it's always there when you see talks done in Zoom, and it's like, I don't know why I should turn it off. Yeah, good. And so in this paper, for example, what we did is that we asked, okay, what are the priors that you can insert in an optimization toolbox so that then you can actually perform the task well, right? And in this paper, we had a prior. So we had a prior that controlled the weight function within a nerve model, right? So this PDF that controls how to integrate color along the ray. And the simple prior that we had is that we simply said is like, I would like a model where faces are not made of smoke, but instead they're just made of empty space or of solid surfaces, right? Because skin is mostly solid. And this worked really well, right? And giving like you really sharp geometry. This is actually learned single shot from a single image, and it works particularly well. And the interesting bit is that if you compare now like GAN-based systems to like purely neural field-based systems, for now, I find the optimization landscape to be a lot easier to navigate than the one created by GAN. So just a bit of a advertisement against that, but it's unclear whether that will hold in time. And people have followed up, right? Like I think after a week and a half after we sent this out, then of course NVIDIA sent out something trained on GANs. But if you then, and the results look amazing, right? G3D just scooped us big times, just in terms of plugging in a GAN and having the results look like truly amazing. But if you now look at the images that you have right there, right? Within this architecture, the heavy lifting of getting actually these crisp details that G3D makes G3D look so amazing is not done by a 3D model, right? It's done by a 3D model. It's done by a supervised model. If you look at those results, minus the background, they look very similar to the one that made in London, right? And so like the two systems are now, I don't think we have cracked yet on how to get super crisp results in 3D models, but I think it should be possible to do that. And so, and the way to actually do this is actually by rather than having a single function representing global, is to actually perhaps focalize your attention to small parts, right? Because this function that you see right here, this function that you see, a video for our stuff. Yeah, this function that you see right here, they might be a little bit smooth, right? From the point of view of a full face, but now shrink the complexity of the function to a small spatial extent. And that's now a high frequency function, right? So there is the representation power to do. That's the angle log trick, right? Like the duality in between scaling in time and scaling in the frequency domain. That's what gives you that. And nobody has actually touched this yet. So please like fix it, because I don't want to use GANs or diffusion models. I think actually you can just get by with a neural field and call it a day. We did more work in this area. So we were, with Daniel. Daniel was finishing up his student researcher position at Google. And we said, well, okay, LolNerf worked pretty well. Yeah, the GAN stuff, we're going to fix it. We care mostly about the face map itself. So it's fine. Can we make the data set 10 to 100 times larger? Okay, because we can. And if you do that, probably you need to have a more powerful decoder, a larger latent code. So what happens? And it turns out that if you scale things up, things start to choke. So MLP don't particularly like to scale to extremely large networks and extremely large latent codes. And so the question that we were asking ourselves was, what kind of structure can you put on the latent code Z so that this enables scalability? And we did a couple of works after LolNerf. The first one is ABC, attention beats concatenation, and the title says it all, right? And sadly, again, transformers win. So across the board of things that we tried, you replace a concatenation MLP with an attention-based neural field decoder, and your PKSNR goes up by 2 to 4 dBs across the board, right? So if you're working in this topic, this is actually an architecture that we introduced at CVPR last year from from scene representation transformers, from Mehdi and my team back at Google. And here we kind of chopped away the encoder. We only focus on the decoder and asked us, is there a better decoder than the one that everybody else is using, right? So that was confirmation number one. And then this year we have another one, which is from, oh, sorry. Yeah, I forgot. I'm an in-person guy, yeah. And this year we have another one where rather than having a single set of latent codes at a single layer, we actually have a progressive representation, right? We can have a chain of codes and you can have T blocks of it. And this is necessary for representing like large spatial extent scenes. So this is a work from Tanga at SFU, and we're actually using it for localization, right? So you can have a large set of codes that represent the scene at different depths of a transformer rather than the very end, and that's it. So this gives you, like, so this is the autodecoder setting. And I hope I've convinced you that if you move away from encoder-decoder architecture and you're allowed to do optimization and test time optimization, then in theory, you can push this likelihood term to perfectly reproduce the input images, right? So you can reproduce the signal. And now the only thing that is left, if you can get that loss to zero, is any knowledge that you get from these likelihood of the model, right? But now the question is like, the model that we were using in LulNerve, which is actually no model, it was an inductive bias due to initialization, but you can imagine that the inductive bias was like, I want my latent codes to be a Gaussian ball around the origin. Turns out that it was a Gaussian ball, not in the origin in LulNerve, but it's the same, it's exactly the same. So this P of M just says that basically shapes are compact, right? And the humans kind of all look the same around a single mode. That was the only inductive bias that we used. And so the question becomes like, is that the final frontier, right? And then that was at a time when the first hits on diffusion models came out, right? So there was the Imagen and DALI 2 era. And so we asked is like, okay, well, perhaps there is a way of not splitting the workload in this way, but saying, close your eyes, pretend everything is well, and let a giant model take care of both of them simultaneously, right? That's what I call this meta learning. Because from my point of view, a diffusion model is nothing else than an unrolled optimization problem, right? And this unrolled optimization problem is capturing both the data dependency as well as the prior or the distribution that you're trying to encode, right? So to me, diffusion models are doing math, like there's no, at least conditional diffusion models. And so that's what we did. So this is actually 3D. This was presented in Rwanda, which I would have loved to go to, but I didn't, a few months ago. And these are actually single shot results, right? So these are actually trained on augmented versions of ShapeNet, like rendered with a photorealistic renderer. And if you compare the quality of the reconstructions to the one that I showed you earlier from encoder-decoder architecture, they are insane, okay? And not only they're insane, but this level of fine level grain detail is done without any nerve process in the way, right? There's no nerve involved in this particular project. There is still a little bit of 3D reasoning. So this is what the architecture, the basic structure of the architecture looks like. So we have a diffusion model. The core of the diffusion model, you can think of it as being a conditional diffusion model, where you have the image you're trying to denoise and the corresponding target, and then you have a conditioning image. This will be like your likelihood term, right? Like, please generate something that matches whatever I have in input. And then the only thing that you give it is that, well, to go from this image right here to this image right here, you explain it by a relative transformation. Okay, it's the bare bone of 3D, right? That's what 3D is. If I change my viewpoint, the content changes slightly. That's literally as little 3D as you can put in an architecture. So this is throwing your hands in the air, saying, no, I'm not going to do nerve. I'm just going to give you the core key idea of 3D, the fact that a camera pose exists, and that's it. And then throw really your hands to the air and train a giant model. This is trained in an autoregressive way. So what do you do? Is that your model? Is there some water around? Maybe not. I ran out of liquids. All right. What you do is that you train the model in an autoregressive way. So before, when you were training a nerve-like model, you have a collection of parameters, right? And you're optimizing them across your training data. Here, on the other hand, your model, this guy right here, is a collection of, this guy right here is a collection of images, right? You're not doing nerve. You're just generating a collection of images that will correspond to a certain camera pan. And so what you do is that you have to generate this collection of images progressively, right? So what you're doing is that you're saying, well, conditional on this image, what will be a reasonable image from this novel viewpoint? Make sense? Okay. And then you grow that set over time. And to make sure that the data is 3D consistent, you can do this stochastic conditioning process where at every diffusion step, you pick a random image from the set that you've currently generated. So in the first step, it's always the first image, but as you generate more and more data, you're asking the model to be self-consistent. Okay, there is an interpretation of this as a constraint satisfaction problem, but in a continuous way, which I think is really cool. So if you want to connect like things from, thank you so much. Yeah. If you want to connect these to like constraint satisfaction in physics to diffusion models, I think there is something to do there. I'm just going to give you a hint on what to do. And the results that you generate, these are actually, so the model was trained, so this giant green, well, this module right here was trained purely by trying to recreate images from another image. And the model actually can generalize to completely out of distribution data. These are actually real images that we just took off the web, right? With the same characteristics that you will have from a photorealistic render, it's like white background that has been chopped up. But this is in full generalization mode, right? These are not only not within our data set, these are actually photos for which you generated a 3D model from. And so this is what scares me a little, to be honest, right? Because I was a hardcore part-based representation person, but then you see diffusion models both in 2D and in 3D being able to do that. Okay, and this scares me a little because I might be out of a job in a few years. Yeah, because it's then you're gonna like. There was actually a panel yesterday at the Area Chair workshop about whether industry is gonna swallow us up all, and then basically we're gonna be at the mercy of the big corporation in working on 3D deep learning. And this is another example of doing it from text. So from text you generate an image. This is done with Imagen, and then you can actually get a 3D model corresponding to it. And yes, there is a bit of jitter and it's not 3D consistent, but there's been now half a dozen extensions of this since May that have addressed the problem, so I can just refer you to those. Okay, so now this gives you like this view, right? So you want to do inference from few shot. So now you can interpret it in a Bayesian way as a map problem where you want to respect your data, but you want to have some prior, right? And to be honest, I don't think, let me just actually drink for a second. That's so dangerous to put it there, though. I fried so many laptops this way. Yeah. 3, I think I'm right now. Yeah, because it ends with Italians, right? It's just I knock everything off. Yeah. All right. So now the question is like, perhaps diffusion models are not the final goal, but the fact is that you have this map way of thinking about problem is still there. And so a completely valid question is like, you can make a choice here. You can make a choice here, or perhaps you keep the two choices together. What is the best choice, right? And if we get it right, and you get something that is extremely powerful, then you get a foundation model for 3D, right? And so now the question becomes, which is all the rage right now, right? Every talk I hear from 3D people now has foundation model in the title, and all of the VC pitches are the same. And so the question becomes like, what does that foundation model look like? And I'm going to give you some hints. I'm not going to give you solutions because I have no idea what's the right answer, but I'm going to give you some things that I consider exciting. So for example, this is a paper that is not present in a CVPR, and a CVPR people, you should also open up SIGGRAPH once in a while. And this is a paper that I love. Like this is from Andreas Geiger's team from Tübingen. And the idea in this paper is that they try to build essentially this prior as a dictionary, right? So back from compressive sensing. So you can say basically your functions live in a submanifold, and then you want to stay close to the submanifold when reconstructing a new piece of data. And you can see right here, right, in this diff is this dictionary field model, that this model, by the way, is trained with few shot images, right? Only, I think, 5 images, if I'm not mistaken, to generate this result. And so basically optimizing within a dictionary allows you to have strong generalization, but still in an optimization-like setting, right? So this is map. This is map where your prior is a collection of dictionary. And this is part-based learning as well, right? Because that P of M is nothing else than a collection of basis functions scattered in space that connect to each other to build something larger, right? And so basically the key message that I want to give right here is that a few years ago, I was thinking about adding explicit parts, take an object, break it down into parts, and then do something. And I've completely moved away from that. And I went into the implicit part-based composition side of things, right? Where you're basically saying space as a collection of features and things that have some internal meaning. And then the dot product or the distance in between the features actually tell you whether 2 points in space belong to the same entity. So it's a continuous representation of parts versus a discrete representation of parts, right? And this, again, as I was saying earlier, removes a big challenge, which is the one of having discrete optimization to deal with, right? You don't have to do anything discrete anymore because now I don't have a set of K parts anymore. I just have some continuous thing where the distance in the latent space tells me I'm doing the right thing or not. And then other things that I'm kind of excited about is also controllability. So this will be like, again, more like part-based. So it's at the intersection of NERF and conditional neural fields and GANs. So these are some pretty cool results from 3D Front, actually, with SP. So look at that shameless plug, yeah. But the thing that I'm actually super interested about is that we actually had this work with Eric finished a couple of weeks ago. And there is a lot of structure within pre-trained models, right? So the concept of part, the concept of affinity, the concept of correspondence, how to take a new model you've never seen before and map it to some centralized knowledge, like, for example, from a picture of a person to a deformable face model, right? That requires like a part-based understanding and a correspondence understanding. And these diffusion models actually have this concept of attention, especially in the latent diffusion way of doing things, that contain a lot of this information, right? So this is a first win. We were using it for zero-shot image correspondence, but now the question becomes: can you now build, like, this continuous part-based representation that allows you to do anything, but you do everything just in this continuous latent space? And that's exactly what is happening here. This is global, but then of course you can do it at the local level. And then finally, this is like the doom. Yesterday there was one of the program chairs is Russian, and she had this a number of times she made this joke that she has this way of seeing the or maybe Ukrainian, I forgot. Yeah, that's a big but yeah. Anyway, she had this doom way of representing the world where everything will be swelled up by a giant model, and we're just going to be at the mercy of some large company that does it. And to be honest, I'm not sure it's possible that just having an enormous architecture just understand what it means to change the camera and understand internally the concept of compositionality. That might just be the thing, right? And if you actually look at some of our past papers, you can actually take these pre-trained models and then probe them. For example, scene representation transformer, you can do that, right? You can take a pre-trained model, feed in a new image, and then try to say, okay, what did you understand internally in this giant model to then recombine a scene, right? And this is something that we're looking at actually right now. And I'm done, 47 seconds over time. Yeah, just want to thank, so here are the first author of the 3 main papers that I covered today. There is probably about 100 people involved in this talk, so I don't want to flatter too much, but they are amazing, so you should hire them as soon as you can.
I'm sure.
Please don't, because they mostly still work with me. So.
I'm sure there are a lot of questions for Andrea. We have time for 1 or 2.
Just one question on the diffusion of those images. Like in actual 3D, does it explicitly come out? It does not, right? You need to do other things in that paper.
So the collection of images is 3D consistent mostly, and then you can feed the collection of images to for example, a NERF pipeline to get a single, fully 3D, like deterministically 3D consistent model out of it.
So it's implicit 3D in it, right?
It's implicit 3D, yeah. That's right.
This prior that does not, it only encodes appearance and deformation, but it does not encode the global 3D.
Yeah, exactly. Yeah.
Do you want both? Or
we were actually working on it, and then Daniel got lured in a startup, so for a while left Google. Now he's back with us, so keep tuned. But there's been a few works since when he had left from other people that actually more or less integrated that idea together within a NERF model, right? But the interesting bit is that there is so much structural understanding in these models. It's crazy. Like you see some of these results, compositionality is a thing, right? And so the question becomes is like, why does it happen and how to exploit it and how to drive it, maybe. But you cannot ignore these models anymore. I was for a little while, and as usual, there was a mistake. Yeah.
Okay. If it is a very, very quick one.
Yes, very quick one. So what is the missing ingredient so we can give a bunch of images to this NERF for diffusion and get like SFM results or NDS results? Right now, they are like still prep of this. Like what's missing?
Scale.
Okay. You need data.
You need 1,000 to 100,000 3D scenes with a lot of images. We have them, right? Like autonomous driving, they already collect those images as they need to drive around and record. but we need like, algorithms to be able to train at extensive like geometric scale, like large without issues, and then share the understanding across scenes. And then a giant cluster to stitch it all together. Most of the ingredients are there.
Let's all thank Andrea for the great talk. Thank you.
Sorry for the.
No, I'm sorry for the mess.
No, it's okay.
Would you like to come up? So we have a slight modification in schedule.
Anything fun? No.
Okay. Can
Yes, we can hear. Yeah.
can you write?
I sent you the main slide. Actually, I can use the laptop.
But I don't have a keynote.
No, it just PowerPoint.
I don't have PowerPoint either. Okay. Do you want me to send it to you via email?
My HDMI, I have HDMI.
Yeah,
Oh.
but you have also to connect to Zoom. Yeah. Do you want me to send you the Zoom link?
What's this?
Done. And you also have to connect this.
For audio?
Yes. Can, okay. And you also need to connect this.
This?
So sorry.
Okay, that's fine.
Okay.
Yeah, I just.
Yeah, of course, of course. Yeah, let me make some this. You can also sit here. Take this out. Do you want to put it crop?
Yeah, and it has a laptop. Yeah, I can try. I think that's open.
I think it will continue. Oh, and so you need to connect this.
Okay.
Do you want to use the chair?
Oh, sure.
And you also need.
Zoom, right?
Yeah. Can you confirm the people in the present group? By Zoom,
Yes, I can
you
hear.
hear us on
Yes,
Zoom?
yes, 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 I can hear. Yeah, and I can see the slides.
Okay. So creating in the last past years, more and more industries are moving towards creating the 3D digital worlds. Because like in the 3D digital worlds, people can interact with pipeline. So
This, are there questions for one? Let me set up my laptop and you can answer any questions. We have time for one question, if there is any. And I think.
Okay.
Yeah.
So do you plan to add materials to the Magic 3D? Because is it using for example SCF material or is just RGB color now?
So right now in the Magic 3D is just RGB colors, and I actually try to add the materials.
What's the challenge?
The key challenge is that how we model the lightings, and also because like for the reason was because like before the CVPR submissions, I tried to add the material, but it's sort of work, but not working decently, so I didn't put it in the paper. And the key challenge is because even if we didn't have the materials, the lighting is still baked into the textures. And that if we add the materials, like it will not to really cover the clocked materials.
Thank you.
Yeah.
Thank you.
Awesome.
Thank you.
Thank you very much. Okay, can people on Zoom hear me?
Yes, I can hear, but with echoing. Can you hear me? Yeah. Hi, Amir.
Can you please say
I'm
something?
sure that they can. Hello, let's speak. Can you hear me?
I can hear you, but I'm not sure that anyone else.
It seems that Despi cannot.
Can you say something again, please?
Hello, 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 hello.
Yeah, it's good that you can hear us, but we don't hear you. Okay, good news, not only we have technical difficulties. So, what about now?
Hello, hello,
What about now? Can
hello,
someone?
hello, hello.
Fantastic, okay.
Great.
We can hear you. Can you say something?
Hello, can you hear me now consistently?
We hear you from my laptop. Can you say something again now?
Hello, hello, hello.
Yeah. Oh.
Yeah, it seems that the on-site folks have difficulty broadcasting our voice.
Can you say now?
Hello, can you hear? Hello?
Soon?
Yes, yeah, I'm speaking. Can you hear me?
June, can you hear us now?
Hello?
Can you please say something?
Yes, I can hear. I can hear.
June?
Hello? Can you hear me?
Can you ping him? What about now? Can you say something?
Hello? Can you hear me now? Hello? Hello?
Finally. Okay. Great.
Oh, cool.
Amazing.
Great.
Okay. June?
Yeah, so our next speaker will be Amir Hertz. So maybe Amir, you can try to share your screen while I give you a short introduction. I think you probably can directly share. You don't need the host access.
Yeah.
Cool. So Amir is a PhD student in the Department of Computer Science at Tel Aviv University under the supervision of Professor Daniel Cohen-Orr and Professor Rajay. And he is also a research scientist at Google. So he's working on extending image editing capability using generative models and working on 3D understanding generation and editing. And we'll be hearing from him on towards intuitive 3D generation and modeling. Take it, Amir.
Yeah. Thank you. Thank you for the introduction and thank you for the invitation. Can you hear me and see my screen?
Yes, everything is fine.
Okay, great. Yeah, so I will present today some of my works, my PhD works. So mostly in my PhD, I work on 3D representation, different 3D representation for 3D editing and generation and modeling. So my works includes texture synthesis, and this is the left work, on meshes, and also on point clouds, point generation and registration. And we also develop this work on the right for transfer meshes from one shape to another using coordinate-based, adaptive coordinate-based MLPs. And today I will focus on two recent works. The first one, Spaghetti, which is a generative model for 3D implicit shapes, which also learned about the composition. And the second follow-up work called Sense, which we develop a model to control spaghetti using abstract sketches. And I just want to mention a few of my works at Google are not related, but yeah, so they are into the dark side to the images. But if you have a chance, visit the poster on Tuesday, 4:30. Yeah, so the first work I will talk about is Spaghetti, which is a permutation of the title of our work, editing implicit shape to part-aware generation. So Spaghetti is a 3D generative model that turns unsupervised 3D decomposition over generated implicit shapes. Using this model, you can mix between different shape parts and further edit the generated shape using just simple transformation, local transformation. So how does it work? Our network has three main subnetworks. The first one on the left is the composition, middle one mixing, and the third one on the right is the actual shape, occupancy network shape. So the decomposition decompose the global shape on the left, Z, into distinct part vectors. This is T, such that each part represents a single Gaussian, and the whole collection of parts represent a Gaussian mixture model. And we train this decomposition network over a large number of shapes using the log likelihood loss between points sampled inside the shape and the Gaussian mixture model that each shape outputs. And this is how it looks after we train it over many, many shapes and the corresponding surfaces of those shapes. And next we learn, next we process those parts vectors using the mixing network, which is simply a transformer encoder. And the last part is the occupancy shape, where we have a coordinate x in the bottom that attends to the distinct shape, distinct parts, vector parts, and it outputs a label, occupancy label y. And it trains, again, using a supervised sample points inside and outside the shape using binary cross entropy. And important part of our training is that we mask, during the training, randomly mask different parts. And it looks something like this. We have different vectors that correspond with different parts. And we mask part of them, and the output should correspond to the same part that we didn't mask actually. So in that way, we guarantee the locality of the information that each part vector holds. And during inference, it allows us to mixing between different parts. So the last part, which I will not cover in this talk, is that we apply affine transformation. And in that way, we can apply on both the different parts and the coordinates point. And in that way, we can apply local transformation during inference. So during inference, we omit the composition network, and we can mix between. We start with parts that correspond from a single shape, and we can replace shape parts by replacing the corresponding embedding with part vector from another shapes. And this is the first application. And we can apply transformation like rotating, scaling over different parts. And in that way, we can apply local transformation. And the next work I will talk maybe briefly today. It's a very recent paper we published, SENSE, Sketch-Based Implicit Neural Shape Modeling by first author is Alexander Inger from ETH. So in that work, we focus on learning to encode 2D sketch into the embedding of spaghetti. And the most important aspects of this work is that we want to handle abstract sketches, and we want to preserve the part level control that we have in the pre-trained spaghetti model. So we can control the output shape using only sketches of distinct parts and not always the whole sketch of the complete shape. So there are many existing works that try to do similar thing, but one thing that we saw that shared between all those works is that they can handle only very high quality sketches, as you can see here. They are not really something that an amateur or a quick, and you can do it quickly using only pen. Yeah. So there are two main aspects of this work. One thing is that we create a very diverse data set of sketches using both synthetic rendering and partial rendering, where we render only part of the shape using the spaghetti composition. And in addition, we create a synthetic abstract sketches using a recent work, Clipper-Saw, which can take a photo and can create a very good abstract sketch from it, which is a very cool paper. Yeah, so I won't cover the whole network, but the main parts are that we have image encoder, which is a visual transformer that output visual embedding. And the next part, we have query for each part vector of spaghetti that should both output the embedding of this part and another classification score that represent if this part appear in the sketch. So in that way, we can also handle like sketches from only distinct parts. And the final network is just give the set of embeddings to the pre-trained generative model and output the shape. And the main application are, of course, sketch to shape, as you can see here. But we can also just start from existing shape and only draw a distinct part and just replace those parts with the existing shape. Or we can start from only some parts of the shape and let the spaghetti model completed like we saw in the previous work. And that's it. That's my talk. Our code for spaghetti is available, and the code for sense will be publicly available soon. There is now the paper in archive.
Nice works.
Thank you.
Thanks, Amir. Yeah, we probably need to jump to directly to the next speaker, Kenny. Thanks, Amir. If anyone has any question, you can reach out to Amir offline. And maybe Kenny, you can try to share your screen.
Yeah, I'll do that.
Yeah.
Am I audible?
Yes, I can hear you.
Okay.
And Kenny Jones is a fourth-year CS PhD from Brown University, advised by Professor Daniel Ricci, and he is broadly interested in machine learning AI techniques to better understand and represent 3D data. So recently, he's been working on combine explicit symbolic representations, for example, programs and neural method in order to generate, analyze, and edit 3D shapes. Take it away, Jenny.
Yeah, thank you so much. Thanks for the great introduction, for having me at the workshop. It's a pleasure to be here. So today I'll be talking about some work on 3D shape analysis over region decompositions. And this is probably not news for this audience, but 3D shapes have structure. We often want to figure out how to parse the structure in a way that's useful for different downstream applications. So given a 3D shape, there are many things we might want to understand about it. For instance, we might want to segment it into semantic parts. We might want to know different motion paths that parts in a shape can take, or we might want to be able to find an editable and interpretable representation of a 3D shape, for instance, in the form of a visual program. So in this talk, I'll be discussing approaches for 3D shape analysis that operate within a two-step paradigm. So first, a shape is going to be decomposed into regions, and then these regions are going to be provided as input for a shape analysis method. So instead of end-to-end learning over the atomic elements of 3D shapes, like points in a point cloud, the methods in the second step instead search over shape regions. So why might we want to do this? Well, if you're successful in the first step and you find a useful region decomposition, it greatly simplifies the second step as the size of the search space gets greatly reduced. And having access to this tractable, discretized state space is much more compatible with a wider range of search algorithms beyond just gradient-based optimization. So how do we actually get useful region decompositions? So this is a core problem at the heart of computer graphics and vision, and many families of approaches have studied it. So traditionally, right, this would be done in kind of non-learning based frameworks that would leverage geometric properties of input shapes. More recently, with kind of the takeover of learning-based systems, a popular approach is to use end-to-end networks that globally learn part decompositions when annotations for the task and category of interest are available. And an alternative, increasingly popular strategy is to instead employ a learning-based method that attempts to represent a 3D shape as a collection of simple primitives, for instance, cuboids or convexes, or even more general local neural networks. And these approaches are great because they can train in an unsupervised fashion, avoiding the requirements of fine-grained label annotations, but their reconstruction-based objectives are often prone to missing fine-grained parts, and finding good solutions in this spaces often requires complicated regularization terms during the objective optimization. So instead, I want to talk a bit about a different approach that our group has developed for this problem called Shred that we presented at last year's SIGGRAPH Asia. And the main motivation of this method is that there are some domains of 3D shapes that have abundant fine-grained annotations in data sets like PartNet, for instance, lamps and chairs, while other categories of shapes have much less fine-grained annotations available, like earphones and faucets. And in Shred, our idea is that we want to learn over in-domain shapes from these data-abundant categories, and then find policies that generalize out of the box to shapes from these out-domain categories. So how do we actually learn a policy that generalizes in this way? The intuition we had is that while reasoning over global part segmentation is really domain-specific, the local part segmentation task actually looks very similar across different domains. So in Shred, we learn these 3 shape decomposition operations that are only allowed to reason locally. So we have a split operation that learns a network that breaks a region into subregions. We have a fix operation that learns a network that, conditioned on a local region, better aligns and fixes its boundaries with neighboring regions. And then we also have this merge operation, which learns a network that considers neighboring regions to decide if they should be combined or be kept as separate parts. And so we find that Shred's locally learned operators, when they're trained on these data abundant in-domain categories of shapes, learn to produce region decompositions that well match fine-grained part instance segmentations, outperforming alternative approaches with respect to AIOU on test set shapes from in-domain categories. But perhaps more interestingly, we also find that Shred's policies, because of this local bias, just generalize out of the box much better to kind of shapes from out-domain categories over comparison methods in just kind of this zero-shot transfer learning type paradigm. So jumping back to the big picture, once you actually have shape regions, what can you actually use them for? So take a task like semantic segmentation. When you have shape regions, the goal is no longer to label the atoms of the shape. So for instance, like points in a point cloud, but rather to give a semantic label to each of the regions. We've actually developed an approach within this paradigm named NGSP, the neurally guided shape parser, which we presented at CVPR last year. And NGSP uses two types of learned modules. So one module, the guide network, learns a neural prior over likely semantic labels for each of the shape regions in isolation. And we can treat this guide network as kind of a local approximation of the posterior and use it to importance sample a large number of possible label assignments to the input shape. Then we can have another set of learned modules to form a likelihood function where different subcomponents reason over either properties of the semantic labels of the grammar or properties of groups of regions implied by a given label assignment. We can then take each of the proposals from the guide network, evaluate them under this learned likelihood, and then select the highest probability assignment within the set as kind of the output segmentation. So if we want to run NGSP over input shapes, we can first find a region decomposition using a method like shred, and then we can use NGSP to find a high likelihood label assignment over the shred created regions. And comparing the predicted semantic segmentations to human annotations, we found that this two-step approach creates much improved predictions over using end-to-end networks that don't use shape regions, but instead try to find fine-grained semantic segmentations over shape atoms directly. And I also just wanted to mention this related work, HAL3D, from some folks at SFU, which is a really great system that proposes a labeling interface using hierarchical reasoning and active learning to create human quality fine-grained part annotations, like those found in PartNet, with much less human annotation time. And kind of critically, just like NGSP, they search over shapes that have been already decomposed into regions, which greatly constrains and makes tractable this really hard search problem. So switching gears a bit to another shape analysis task, we've also investigated how region decomposed shapes can be used to improve visual program inference. So we developed a method, ShapeCoder, which we'll be presenting at SIGGRAPH this year, that takes in an input data set of shapes represented with primitives. And then it automatically discovers a library of abstraction functions, and then also infers visual programs that use these abstractions to compactly explain shapes from the input data set. So these discovered abstractions capture common patterns, both structural and parametric, so that programs rewritten with these abstractions are more compact and expose fewer degrees of freedom. So for instance, the orange and purple abstraction shown here can be broadly applied across different input tables to explain the same structural concepts, even if those components are expressed with diverse geometry. And moreover, having access to this programmatic representation with abstractions supports downstream applications like shape editing directly, as the parameters of the inferred program can be modified to explore a family of related shapes. And once again, to solve this hard problem, that of finding a library of abstractions and programs that use those abstractions that's specifically tailored for a given data set of complex 3D shapes is only made tractable because we assume that each of these shapes is decomposed into primitive approximated regions. So now that we've talked about some different approaches for 3D shape analysis within this paradigm, I wanted to offer some thoughts on interesting future directions. So as I've mentioned a couple of times, performing shape analysis over shape regions provides an opportunity to employ more powerful search algorithms. And while some work has been done along this direction, I think pushing this line of investigation further is a really great direction. So one recent example here that I really liked is this split, merge, and refine work out of KAIS, where starting with shape regions produced by BSPNet, they employ a Monte Carlo tree search along with some continuous optimization in order to find a set of tight-fitting bounding boxes for a 3D shape. Another benefit of operating within this kind of two-step paradigm is that a broader class of objective terms can be employed, as unlike end-to-end systems, not all of the terms need to be made differentiable into loss functions. So we explored this a bit in NGSP, where we learn a likelihood function that we run discrete search over. But I think this paradigm opens up even more extreme possibilities, where, for instance, part-to-part relationship rules influence the likelihood function. And as a motivating example for why we might want to do this, human labelers of datasets like PartNet were given both rules and examples for how parts should relate to one another. For instance, in the definition of a back frame, it should outline a back surface part. And I think there are opportunities within this paradigm to give the same kind of information to shape analysis methods. And finally, I also just want to note that the task of finding a good region decomposition is far from being solved. In fact, you might argue that the exact type of regions you might want could differ depending on the downstream task you're working with. So an interesting question here is whether region decomposition methods can be made aware of these different downstream requirements. So for instance, in Shred, we apply these local operations in a fixed order to produce decompositions, but maybe a meta operation scheduler could be employed to apply additional operations based on feedback from the shape analysis method itself. So as one example, if a semantic labeling method identifies under segmentation in a region, the shred split operation could be called to further decompose it. And as a closing meta comment, I think really successful methods within this paradigm will need to have kind of an open loop communication between how regions are produced or modified and how those regions aid search for the downstream shape analysis task. And yeah, thank you so much for listening, for having me. Thanks also to my great collaborators at Brown, Adobe, UCL, and UChicago. All of the papers, project pages, and code for the approach I talked about can be found on my website. And please feel free to reach out afterwards with any questions. Thanks.
Cool. Thank you so much, Kenny. Yeah, so moving ahead to the next speaker is Mika. Are you here, Mika, on Zoom? Thanks, Kenny. It's great to have you.
Yeah.
Is there any question while we wait for Mika?
Hello, can you hear?
Yeah, I can hear you.
Okay,
Cool.
wait.
Can you
and
share your screen?
Yes, let me first connect to the one at a
Yeah,
time.
take your time. Yeah.
And
So Mika is currently a PhD student in the Department of Computer Science at Stanford, advised by Professor Leonidas Gibas. She is generally interested in computer vision, graphics, ML, particularly focusing on the representation and generation of 3D objects and scenes, and have a couple of works on mesh deformation, CAD modeling, and the neural implicit fields. And her research goal is to achieve high quality photorealistic reconstruction and user controllable 3D generation. And yeah, we can see your slides. Go ahead, Mika.
Never mind. All right. So the title of my talk today is Towards Controllable Scene 3D Content Creation by Leveraging on Geometric Priors. So one goal of learning structural and compositionality of data is to achieve automated 3D content creation that would otherwise be tedious or laborious for for users. But a key property that is important for content creation to be useful is user controllability. And for example, a user might want to plop a desk a lamp on a desk, but then not you want to be able to control what you're generating such that it is an appropriate let's say object that is coherent with the scene. Or let's say you want to put the chair on a beach and you want a particular style that would fit the context of the scene. So there are various forms of user control. Is there? Never mind. So previously, we explored different works that enable user control, such as conditioning on target scans, or even programmatic edits through CAD. In this talk, I would particularly be focusing on two works on enabling control via semantics for objects and sparse input views for scenes. And to enable this, I would be talking about leveraging on two different types of geometric priors. So first, semantics for objects is I'll be first talking about de facto, a very recent work that is led by George. George is an undergrad that I mentor in Stanford, and just a special shout out, he will be applying for PhD in the next intake. So it is controllable part-based generation with cross diffusion. And so the prior that we are leveraging here, the geometric prior is semantics. And modeling semantics enables us to have explicit user control. And this this allows us to have like semantically meaningful norms that allow for fine-grained edits, such as like resampling different parts while keeping other parts fixed, or sampling different configurations or transformations of the parts. So we want to model a generative shape latent space that allows us for these like fine-grained control. And in contrast to like, let's say, existing works wherein like you model the whole shape latent space as it is. So when you sample, you can achieve like, let's say, all the very different types of chairs that may not be suitable for the scene that you are trying to create. But so it has limited usability. However, like with like controllable generation in parts, we are able to better adapt what we want to create for the particular context. So first, like we want, before going into the method, we first talk about like how we represent objects. So objects that we represent are decomposed into part styles and part transformations. So for any shape S, we first have its like, we first model its canonicalized parts, or what we call part styles. And conditioned on these part styles, we have for each one of them, there are transformations that will lead to like the output shape. So the canonicalized parts is basically factoring out the transformation being scale and position, and inherently just capture like the geometric or structural or topological properties of the semantic part. And then the transformation is like taking these canonicalized parts and then fitting it into like a coherent object. And why, like one side note on why this is not too straightforward is actually if you're given canonicalized parts, there are multiple explanations on like, for example, like each of the colored points here represent one part. So there are multiple possible transformations that will output a coherent or valid object. So we need to be able to learn how to capture these variable modes, wherein like in our data, we might only have one like discrete samples for each particular shape. So concretely, in order to take this representation and put it into the method, we propose a factorized joint prior. So instead of having a prior which is on the whole shape space, we have a prior that is a first modeling independent part styles, or P of Z, and then conditioned on these part styles, we model the transformations. And the inherent assumption is like for each part style, we have like independence, which means we can sample each different style separately. And then we have a conditional distribution that conditions on this set of like canonicalized parts to output different transformations or variations of the particular object. So in summary, de facto proposes a shape space factorization that enables, that decomposes shapes into part styles and part transformations. So P of S, which is the shape would be factorized into these three components. And in summary, because time is short, like there are three components, which is the part stylizer, the transformation sampler that we talked about in the previous slide. But the crux, or one key component of like in our contribution, is this cross diffusion network that allows to model the to stitch both the style and the transformation together to output a coherent shape. So it views shapes as like a joint distribution of like styles and transformation. And the idea behind this method, so it is a transformer-based architecture, but we also reformulate or like generalize the forward diffusion kernel. So instead of having one Gaussian ball that plops into a whole shape, we have, like, as you can see in the figure, multiple balls that are transformed, like related to the part transformer, and then outputs like a coherent shape in the end. So because of all this, like with this design, we show like different applications that allows us for first like part level sampling. So we can keep like anything that's gray is something that's kept fixed, and the colored points refers to something that we resample. So we can keep parts fixed and resampling other parts and still create like coherent shapes. Or we can even like resample all other parts while keeping one of them fixed. So in the right, yeah. And this like we showed that in different metrics that we can beat like existing baselines in like point cloud generation. Another application is like transformation sampling. So with fixing the part styles, we can resample different transformations that will create variations of the shape, as shown here. Then we also have like part level mixing. So taking one part from each of the shape and then how do you stitch it together to create like a coherent shape? And like we can compare with existing work such as like Amir spaghetti or like a modified version of ShapeGF and Lion, and show that because we are modeling the joint distribution of parts and transformations, we are able to output like a coherent shape that are like connected. Yeah. And then we could interpolate like a particular part latent space as shown here. So we see that as we interpolate through like a single part, the other parts can co-vary or adapt to snap the shape together and output still like a plausible output. As shown like by the lamp head, as we make the body thicker, like the head is also like adjust accordingly to make the output consistent. And we can see that there are different, as we interpolate as well, it keeps itself to the valid space of shapes as shown by those like discrete jumps of like the airplane and the chair. Yeah. And then I would like transition a bit to a second part of like a different mode of control, which is instead of like object parts is like we have sparse input views. So from objects, we also transition to scenes. And like this is like viewing like 3D content instead of like an explicit representation as shown in the earlier work. So this is a coordinate based or a neural field type of presentation. So this is a work that will be presented in CVPR. So please come into our poster as well. So it's SCADE, which is nerfs from space carving with ambiguity-aware depth estimates. So given sparse input views, we are also, if we want to create like 3D content, in this case represented as a nerf, how do we use sparse inputs to constrain the optimization? So because the inputs are sparse, like you want a user to like only snap a few images of the scene and still create this, like recreate or reconstruct the 3D scene. But because of its under constraint nature, we have to leverage on a geometric prior. And the prior that we leverage on is monocular depth estimation. However, like monocular depth is, so monocular depth is a generalizable prior, meaning there are a lot of pre-trained models that are on diverse large data sets that allow us to like capture different structures or like geometries of the scene. However, we know that it is inherently ambiguous. So given a single image, there are multiple plausible explanations of the particular scene. Such ambiguities arise from like albedo versus shading, scale, or even non-opaque surfaces. So now the question becomes, because it's ambiguous, how do we handle this ambiguity and still model or still leverage on this prior to create the scene? So in contrast to existing monocular depth works, we instead represent depth as a distribution instead of a point estimate. And in order to do this, we utilize like CI-MLE. So in like given an image, we take a state-of-the-art monocular depth estimation network, in this case, LeRez. We add the latent code or use the CI-MLE technique, which is a simple addition of like a set of added-in layers to instead produce a distribution for depth. So now this is what we call our ambiguity-aware prior. And this allows us, what we see is like to model the different ambiguities inherent to monocular depth estimation, such as like albedo versus shading. So you could see like on the door frame, you have like different samples modeling the different ambiguities. And then you have like scales of concavity, such as how deep or how curved the sofa is, and non-opaque surfaces such as like glass through a glass, wherein you could see that certain estimates shoot through the glass and certain other estimates like terminate at the glass. So using this, we are able to, like, given sparse input views, each of these sparse input views would have its own set of depth hypotheses as shown. So you could see like we really model like different discrete mode jumps. However, they are still valid. Now the issue is like, how do we disambiguate or like make it coherent in a 3D representation? So we resolve these ambiguities by fusing these information from the sparse views through a NERF. And the key idea of all of this is to utilize like classical space carving. So our approach is a probabilistic analog to this classical technique, which is like, so now like, let's say given like two cameras, for simplicity, let's say each of these two cameras have like two different hypotheses. So now how do we resolve or like pick hypotheses that are consistent or coherent across the scene? Is like one, you could imagine like, let's say this depth hypothesis, like green 2, is not consistent with either of the two yellow hypotheses. Because if it were, then there should not be like the space on the green cone should be clear. So that is like the analogy, intuitive analogy to what we do in our losses. But using this technique, we are able to like fuse the different information from multiple views given a nerf. And the summary of the pipeline is given sparse input views. We extract our depth estimates from our prior, and then throw it into a nerf with our proposed space carving, probabilistic analog of a space carving loss to generate, like to reconstruct the 3D scene and create like, let's say a scene content conditioned on input views. And yeah, and these are more results, but we could talk more in detail in our in the poster session on Thursday. But yeah, thank you. And this code for SCADE is released, and paper for both and project websites are all online.
If you have any questions for Mika, go to her poster and ask her.
All right, shoot me an email.
Angela can go
start
next.
setting up.
We can see the screen, but cannot hear.
part of life is principle now to our perception tasks. How do we perceive 3D from just a single RGB image? So this is very ill-defined because we have only the single view of the RGB colors. And we see a person, you can possibly recognize many of the objects here despite being only one view, despite having many inclusions. And so we need to understand these strong 3D colors in order to understand the structure of the objects in the environment. So we can look at very strong 3D colors, for instance, videos, shapes like ShiftNet, HeartNet, and retrieve and align them to the image. And thus to understand how the objects in the image are structured. So we can do this by basically looking on 2D segmentation methods, which we further now quite powerful, and to extract out the detected objects in the 2D image, invite them into a joint embedding space with the 3D models. Here, there's a bit of a delay back there, so we're actually looking for within this embedding space that the RGB observations and the 3D shapes are placed together if they're structurally similar to each other. Regardless of them, from a different kind of domain, and then you can work out the translation and visualization of the objects actually we're seeing in the image themselves. So we can compare this embedding space with feedback learning, in particular with the use of compact blocks. And that results in an embedding space that looks like this with the TSM visualization. So if we do end up with clusters, for instance, in the top left, we have sort of round tables, and then bottom we have a picture that are clustered together by structure similarities rather than by appearance features. So that allows us to retrieve by querying a new RGB observation into the embedding space and pulling out the nearest neighbor 3D shape that represents the object. And so here we have this nice property of being able to understand the structure of 3D objects up to the validity of the data set. So all of these objects are going to be physically plausible and valid when retrieved and aligned to the image observation. Of course, those can be extended even further for more challenging environments. So here, actually, this kind of image from stagnant is a bit more like ones that you might see in the wild, rather than ones found in a catalog. And so you have a bunch of exclusions and not visibility of many of the objects in the environment. So if we do a path-based training, we can still end up with these reasonably robust representation of the objects in the environment. On the other hand, there are certain limitations, right? If you are retrieving things from a database, it's a fixed database. So it's pretty much guaranteed to not have the actual object that you're observing in the database itself. So you're just looking for nearest potential candidates. So there's an image of what you see and what's being retrieved kind of nicely represents similar kind of structures, but it's obviously not that here and also not the same here in the environment. But for me, relaxing at the hard constraints of using a fixed database as this required, and learn something a bit more flexible. Okay, and so that goes to learning these manifolds that represent valid shapes and parts. You've seen some of them already in the early talks today that produce really nice kind of decodings of shape spaces, and in particular, we wanted to from the manifold that decode out to these shapes and parts. We wanted to be able to leverage it to optimize actually fit to an input observation. And so from an input, we want to bring that into that manifold and see what is the best that represents what we see here. So that allows for a bit more flexibility than the fixed database with people kind of approach. So in particular, the task we're looking at here, with Brendan's input on the construction on the right-hand side, we want to be able to recognize the objects and their complete composition, including filling in compares arrangements and regions in this environment. So what we do is from this RGB scale at a high level, we're first trying to map into our line manifold of shapes and parts. And so that produces some initial answers for all of the objects here in the environment. even better than that, we can then optimize such that it actually fits the geometric observation that we have in the RGB scan when it's kind of optimization. And we can leverage the fact that we know that we come out of the scene and try to optimize for some consistency. And so that allows us to figure out the shapes from our dimensions that now more accurately represent the input observation. So the way that we the same thing with shapes is pretty simple. So we have coordinate with MLP where is the XYZ coordinate in 3D twins and all has the parts that have the comments including the part count as well as into the MLP to predict the of the part at that particular location, as visualized here for these separate parts of the chair. And so this can be optimized in an autodecoder fashion in order to learn the MLP as well as part latents that correspond to all of the train instances. So here you see FP is the MLP function. It produces a distance value that we can simply compare it to the ground truth SDF values in order to optimize this function, in addition to a regularization on the latent codes to ensure that we have a relatively compact manifold. And in fact, we can do pretty much the same thing for the shapes, since we have no part types. It's just a shape latent and the coordinate that are being input into the MLP to predict the SDF. Again, this is being trained in the same fashion, so that we have latent codes for all the train shapes here. So if we walk through the space that we've just optimized, you can see some of the different interpolations through the part spaces for these different class categories. So here we're moving from just two different types of objects in all of these classes. In fact, we can even smoothly interpolate through a different discrete number of legs, for better or for worse, considering that the intermediate states are not necessarily going to be fully valid shapes in that scenario, but it allows for the flexibility for us to potentially walk through the manifold and find something that better fits the input observation, right? So from an input scan, then we're first going to take all of the detected objects from a state-of-the-art 3D box detector. Use that geometry features in order to predict the set of part types that exist. For instance, here for the chair, the seat, the back, and the legs. And we want to map them now into the latent manifolds. So in particular, this mapping is being trained on just the optimized set of latent codes from all of the train instances, which means that actually, despite being a regression task, it actually operates very similar to retrieval. It's going to put out a code that's very similar to the nearest train shape in the training set. So what you get out looks like a nice kind of shape of a chair here, but it doesn't fit precisely to the input observation. And so now we want to be able to improve that shape code by optimizing the manifold. And so just to help guide the optimization, we also have a coarse estimate of dense segmentation, so that we can constrain the parts to match the input geometry. We also have a regularization constraint that the part and the shape decoding, this is why we predict both parts and shape, are matching to each other, because we want to encourage nice properties like symmetry in the output decoded shape, as well as discourage divergence of parts from each other as they're being optimized. And finally, I think it's kind of nice because we often have repeated instances of the same kind of objects in one scene. We can take advantage of that information that this comes from just one scene environment. And if there are any objects that had decoded out to something similar in the shape latent space, we can constrain them to optimize to a consistent shape decoding here. And so that allows for a much nicer fit to the input observations, as well as more consistent representations of all of these objects, despite the fact that they've been seen from many different kinds of views, and they have different kinds of occlusion patterns. So just to visualize that optimization process, you can see as it's iterating through and trying to fit better to the input scene constraints here. So I think that's kind of nice. We can leverage these learned part spaces and then fit them directly, right, to the input environments. And in contrast to prior state of the art that takes like a single forward pass prediction, that means that we can actually have more accurate shape part completions in these RGBD scans. So perhaps more easily visualized in a qualitative fashion. So you can see in comparison to prior part-based state of the art, we can achieve a better fit to the input geometric constraints of the scene. So here again, and also in comparison to without the scene consistency constraint, this actually helps to get just more information out of all of the objects in the environment to achieve a better representation. So we get a bunch of nice kind of part decompositions now on these real world environments. But can we actually take the same kind of approach and apply it maybe not just for objects and parts, but complete object configurations in 3D scenes? And in particular, since we don't want to rely heavily on limited quantities of 3D data, can we actually learn these kinds of scene priors or parametric scene models without full 3D supervision? All right, so instead we're going to relax the 3D supervision constraint a little bit and say, maybe we can learn from 2D multi-view data instead. So here, basically, assuming that we would have multiple image observations of the same environment rather than the full 3D reconstruction, and maybe we can leverage the semantic information that is now relatively easily extractable from this kind of information. And so we want to learn the same kind of nice manifolds here, now representing 3D scenes and their object configurations, so that we can decode them out to valid scenes. So here you can see a visualization of what we would like, right, to be able to sample multiple codes and produce different kinds of nice valid 3D scene configurations. In fact, potentially interpolate through these codes. Philosophically, this is an interesting kind of question, whether you want the space to be completely continuous, since in fact you would have to appear and disappear objects when we have a different number of objects in the environment, or potentially that objects of different class categories. So you can judge for yourself whether the approach that we've taken matches up with your expectations. And finally, if we learn a nice manifold of these 3D scene environments, then we can use it for conditional generative tasks, for instance, to try to match to an input image and decode out the representative scene in the latent space here that produces a similar manifestation of that image. So in particular, the approach we're going to take is to try to model a decoder that can take in an input latent code, produce a 3D scene, and that scene should be constrained by how well it matches to the semantic information in these 2D images. So in particular, we're operating based on semantic constraints because these ones are relatively robust towards domain differences. Since here we're modeling just object geometries, and in the 2D images, they have a huge variation of color and texture, whereas semantic boxes, semantic masks, should have a very similar kind of distribution across these two domains. So our model is based on a transformer. We first sample a vector from a hypersphere, and we're going to start to generate the scene in an autoregressive fashion. So at the beginning, we have just an empty room. So that's the start token. And the scene context is being learned from whatever we have at the moment, just an empty room. And then we try to decode out the next object in the environment. So since we're operating autoregressively, once we predict the next object, that becomes an input to the scene context, and we can predict the next following object afterwards. So finally, we have n objects in the scene. And we want to be able to produce an actual scene from this set of features. So we are modeling the scene as sort of the layout and the individual object shapes. So in particular, all of these object feature vectors, they're being decoded by MLPs to predict the class category of the object, the bounding box of the object, that these two effectively represent the layout of all of the objects in the scene, as well as the geometric structure of the shape as a deformation on a template sphere mesh. And for representing then the detailed sort of structure of all of the objects in the environment. So here we start training, and you can see the initial scene being represented by all of the default sphere meshes for the objects. And we start to optimize first for the general structure or the layout of that scene environment, which means we're only optimizing for the object class categories and their bounding boxes. And these, when rendered out, should match with the distribution of the 2D semantic box detections. So here, this will move all of the objects into a general kind of structure in the scene. And that will produce some kind of layout that's approximately matching now with our multi-view information from just 2D boxes. And so once we have the layout that has reasonably converged, we can start to refine the actual shapes of the objects as the deformations on the spheres. And of course, these should match with the masks in the 2D images. So that gets the general kind of structure of the scenes here. We can even go a bit further, since this is just sphere deformations. If you want to produce a bit of a nicer 3D scene, we can use the estimated geometry of the objects to retrieve back into a CAD database so that we have a nice CAD representation of the environment. So once this is trained, we can then start to sample 3D scenes from the space. And so these are just a bunch of arbitrary sampled codes in the optimized space. Again, these represented by the retrieved CAD models to the layouts and the shapes that are being produced by the latent code. Here is kind of interesting. We can also interpolate between two samples here from the top left down to the bottom right. And you can see this is a kind of interesting task because we don't have the same number of objects actually in the two samples. So some of them are basically appearing and disappearing as we move forward. And eventually we come to something that's a bit closer to the second sample here. So since our scene generation also encodes basically whether or not these objects are existing, we are able to just suddenly appear or disappear at some point in the interpolation process, the objects. And finally, we can also use the manifold in order to try to look up scenes that represent input images, in particular, again, based off of the 2D boxes and semantic masks that are in the images. We try to find a latent code of the scene that best fits with the 2D semantics that are being observed in that image. So that's kind of cool that we can then reconstruct an estimate of the object structure in this environment. So again, it's not going to be fully perfect. Here you see, for instance, the mask of the TV in the top example was relatively small, and we end up with the wrong orientation of that TV in the scene reconstruction. But we do have approximately all of these objects here. And similarly for some of the chairs, because the masks are a bit small in this image due to the occlusion with the tables, you do end up with slightly wrong orientations of the chairs actually in the reconstruction. So I wanted to also talk a little bit about in depth about potential outlooks in this kind of direction. So of course, interesting aspects of what we were talking thinking about fitting to image and video inputs, I think there's a lot more opportunities here because we're only modeling really the structure and geometry, and actually appearance modeling materials and so on are very important to understanding actually the structure of 3D shapes and also of 3D scenes. And as well as better ways to sort of implicitly learn properties like symmetry or volume constraints that we would like to have to maintain the physical validity once we remove some of these hard constraints like, pure retrieval from a database. We still want to be able to move around the latent manifolds, but we want to preserve some physical plausibility, perhaps without fully modeling the whole physics simulation. Of course, recently we've seen huge advances in language models, and I think there's an interesting opportunity here, not just for editing, but I think because in 3D we have, somewhat limited data. And so language kind of lies at completely the opposite spectrum. We have tons and tons of text and language data, and that might be something that can help to ground the learning of 3D-based features. So that we can leverage more rich kind of encodings and the massive quantities of data. I mean, we also want to be able to take advantage of 3D data that does exist without labels. And for instance, here, we've actually developed an approach to do unsupervised 3D understanding. So without any manual annotations, we can actually start to get the general structures of these big furniture kind of like objects in the environment. On the other hand, I do think there's actually a bit of a hole missing in our understanding as we're moving from shapes to 3D scenes, that going fully unsupervised is, I think it is cool and important, but we're still actually missing examples of high fidelity 3D content to learn the general structures for. So this is also what we're looking at in terms of trying to address the gap for high fidelity 3D information. And in this case, you see the scan from the ScanNet data set, which has clear artifacts in terms of the geometry in the environment, whereas what we're doing now is trying to collect a much higher quality version, ScanNet++, that actually maintains the geometric fidelity that's high enough to represent really the highest fidelity kind of 3D scene data that we could potentially learn from. And just having some examples, I think, of real world environments at this kind of high quality in combination then with all of the more weak signal that you can potentially get from large masses of text and images will help to produce the next generation of methods that can really understand the structure of objects and their geometry. So here we're actually collecting both high-end geometry as well as much higher quality color so that we can understand all of the properties of the objects in the environment. In particular, what this is basically being collected with paired high-end geometry and color, as well as more commodity sensor in terms of an iPhone. So this is from the geometry standpoint, collected with a FAR laser scanner that's got about 1 millimeter resolution in geometry, high-end color from a DSLR, and an RGB stream to represent the commodity information from an iPhone 13. And we've got, we're looking at understanding, the same kind of semantic object structures in these environments. So we have annotations in terms of the objects and their instances that can now be resolved due to the high resolution of the geometry in this environment. So I think this is something that can potentially help to produce signal for new methods that look at really comprehensive understanding of 3D structures here. All right, so currently this is an active effort in terms of collecting this kind of data. So we do have at the moment around 400 scenes, almost 200K DSLR frames. a few million iPhone RGBD frames and a bunch of already annotated class labels and instances. And we're hoping to basically have this as the representative of high fidelity data so that you guys can help to develop the next generation of methods that understand structure of objects in environments. All right, so with that, I would like to conclude. Thanks for your attention, and thanks also to the students and collaborators who really helped make all of this work happen.
We have time for 2 questions.
Andy, I ask, so the motivation for the neural parts priors work, as I understand it, was basically like, well, we can retrieve these 3D shapes, but they're never going to be perfect matches. So we should learn this neural implicit parametric prior so we can really get sort of much better matches to what's in the scene. And one thing I've always loved about these retrieval-based systems is that you can retrieve super high quality geometry so that you can get production quality assets out of them. And when you've gone to this sort of neural implicit model, now you don't have that property anymore. And I know that, like, for example, Mika, who spoke earlier, had this paper on like joint learning to retrieve and deform 3D shapes to match images. So I'm curious to hear where your head's at in that space, about what you think is most important. Do you think there are ways to, bring these approaches together? Just, what you're thinking about that.
Yeah, I in general, I actually like that kind of approach that maintains the high fidelity of the shapes that are being retrieved. It ties a little bit in the context of what I think, and I might be wrong, that it's a bit challenging to learn 3D when your sort of examples of high fidelity data are not that high fidelity in the first place. So when you're learning from ShapeNet meshes and you want to retrieve them, they look great as they are retrieved. But once you want to start to deform them, they become more challenging because these are not really artist quality level of meshes. And so that's part of the reason why then we went straight to a fully, implicit representation, because we have a lot more flexibility in the shape manifold, and it does operate nicely in a continuous fashion, whether or not that's kind of the right approach or not. And so that gave us kind of, I think, at the moment, the better trade-off between flexibility and the ability to represent the geometry there without having to deal with the strange sort of internal representation of many of these objects that actually do exist in data sets that are collected just off the web like ShapeNet. So we're trying to go the other route of trying to get like real world kind of high fidelity data rather than, the artist modeling kind of version, which I think is also pretty cool, but I don't have the right solution to that one at the moment. Yeah, learning about how to generate artist quality meshes without really having a lot of access to them is another kind of interesting challenge there too.
Yes, one more question.
Thanks for this very nice talk. Okay, so I just want to ask, your final result, the final few slides that you show the reconstruction of the TV, but somehow the TV is floating in the air. So I'm just wondering, how do you deal with this kind of occlusion or object attached to another object kind of problem?
So I guess you mean in terms of learning the 3D scene priors, and we don't have any explicit constraints at the moment for sort of the physical plausibility of the environments, right? So we're learning these mostly that they just match sort of the rendered 2D boxes and 2D masks, which is a bit under constrained actually, because you don't have, you have a lot of flexibility of where the object could potentially be that it actually matches the semantic masks. So optimizing to match semantics is kind of nice because it gives you a lot of flexibility to resolve this domain gap between, 3D environment and a bunch of 2D image observations, but it doesn't fully constrain things like support relations or this kind of stuff, which would of course need to eventually be modeled in terms of understanding the full 3D scene graph information.
Got it. Thanks.
Let's all thank Angela once again. Thank you so much. I think start setting up. Because it will also take some time. It gives more. It's fine, don't worry about it. This one.
Yes, I can hear.
Okay, great.
Yeah, but the voice is a bit blurred.
It's a bit like, I'm going to fix this. So let me start playing the video. So the next session is the building challenge. Mother's visual is not good. So we will listen to some.
Walls, doors, windows, and so on. Through the BuildingNet challenge, participants have the opportunity to benchmark their models against a carefully curated dataset and contribute to the advancement of part segmentation techniques in the field of 3D data analysis. Let's now delve into the dataset used for this challenge. BuildingNet is a large dataset of 3D building models with consistently labeled exterior parts. Specifically, it offers 1,849 building models in the form of polygon meshes, which contain 554,000 labeled mesh components corresponding to geometric primitives used by modelers while designing the meshes. Additionally, each model is accompanied by its corresponding point cloud based on the 3D mesh of the building, offering a rich representation of the building structure. So why bother with buildings? Current 3D shape datasets such as Shape and PartNet mostly deal with small-scale objects with relatively simple structure and few number of geometric primitives. For example, the average number of triangle groups corresponding to such primitives is 24 in PartNet, while in BuildingNet it is 26 times larger. This dataset pushes 3D deep learning to large-scale objects with more complex structure. Another motivation is the multitude of applications related to labeling 3D buildings. Structure-aware generative models of 3D urban geometry and texture are becoming increasingly useful in graphics and virtual worlds. Labeled parts can also facilitate style-related analysis of buildings. Finally, synthetic building datasets may also be useful to train or pre-train 3D urban recognition pipelines. Creating this dataset was not easy. Inexperienced human workers can easily mislabel domain-specific parts such as domes or buttresses. On the other hand, hiring experts such as architects to label thousands of buildings would be time-consuming and costly. Another complication which affects human and machine annotation is that building meshes are non-watertight with tens of thousands of polygons. It is hard to label polygons one by one or draw segmentation boundaries on them. An observation that can help us here is that building meshes often have useful metadata, such as groups of polygons corresponding to geometric primitives used during modeling, such as the ones you see on the right. These groups can simplify human annotation and may improve machine annotation. One last challenge is that building parts often vary a lot in terms of size, even within the same building, such as the domes you see here. They can also vary a lot in terms of geometry and texture across models. I will now discuss the human annotation pipeline used for creating the building dataset. First, we mined several thousand of 3D models from the 3D warehouse repository. Various quality checks were performed to remove models with too few polygons, groups, and no texture. We corrected geometry problems, including reorienting the normals and removing the generated polygons from the meshes. We also removed the interiors through raycasting, since our goal was to label building exteriors. We then performed a small-scale study involving architects to label a small set of our buildings and find the most common labels they use. 31 such labels were identified as visualized here, creating our target label set. Our next step was to find human workers capable of performing this task. After worker training and evaluation, we picked only reliable ones from mechanical term. Finally, annotations were gathered by using annotation interface. Our test and evaluation phases offer the training, validation, and test split in a proportion 80, 10, and 10%. The right column shows the total number of labeled components, or in other words, polygon groups per split. I also want to highlight the average number of labeled groups per model in each split of building net. Across the dataset, we observe an average of 635 annotated components per building shape. This demonstrates the richness and complexity of the dataset, offering challenging benchmarks for 3D part segmentation of large-scale objects with intricate structures. Now, let's discuss the two main evaluation phases offering the BuildingNet challenge. In the first phase, called BuildingNet Mesh, algorithms can access the mesh data, including subgroups and texture. In this aspect, they can take advantage of any pre-existing mesh structure common in 3D building models. The second evaluation phase, BuildingNet Points, is designed for large-scale point-based processing algorithms that must deal with unstructured point cloud data without access to mesh structure or subgroups. For each mesh, 100,000 points with Poisson discounting are obtained to achieve a near uniform sampling. For each point cloud, point normals and RGB texture information that originate from triangles are also available. We also offer two demo cases where participants can submit their predictions on the validation split in order to familiarize with the BuildingNet dataset and the online submission platform. The winning participant team of each phase is picked based on their performance in the test split. Now, let's dive into the evaluation protocol used for the building net dataset. The evaluation protocol is designed to objectively assess the performance of the participant models in part segmentation of 3D buildings. Since most part classes are commonly encountered across different building categories, all evaluated methods should be trained across all building categories. Methods must also effectively address the challenge of part class imbalance present in the building net dataset. The dataset exhibits variations in the distribution of different part classes, with some classes being more prevalent than others. Therefore, participants' methods need to be robust and adaptive to handle this class imbalance scenario. For evaluation in the point cloud phase, the metrics of mean part IOU and shape IOU are used, along with per point classification accuracy. For the mesh phase, a variation of the previous evaluation metrics is applied on triangles, where the contribution of each triangle is weighted by its area. The winning team for each phase is selected based on its part IOU performance. To facilitate the building challenge, we leverage the power of EvalAI, an open source platform designed for evaluating and comparing machine learning and artificial intelligence algorithms at scale. EvalAI provided us with a robust infrastructure to host the challenge and streamline the evaluation process. Using EvalAI, we were able to create multiple evaluation phases and dataset splits, accommodating the diverse requirements of the challenge. This flexibility allowed participants to train and fine-tune their model using the training and validation split, while keeping the test split concealed until the end of the challenge. Let's now discuss the baseline methods employed for the two evaluation phases of the building challenge. The baseline methods provide participants with a starting point and a performance reference for their models. For the building net points phase, we tested a classic unit architecture that utilizes the residual blocks. This network was implemented using the Minkowski engine and auto differentiation library for sparse tensors. For the mesh phase, we tested various baselines. One simple baseline is to per sample point on the mesh, then use Minkowski-net to extract per point descriptors, and finally aggregate these descriptors for each triangle. Aggregation is performed by using mean pooling of the descriptors of points belonging to each triangle to extract per triangle descriptors. Then we employ an MLP classification layer to label each triangle of the mesh. We transfer point descriptors to triangles using the architecture that we used in the point phase, yet the performance remains low. Another baseline is to transfer descriptors from points to groups of triangles, which correspond to larger geometric primitives in the mesh. Here we find all points belonging to each triangle group, then performing pooling of their descriptors to extract the descriptor per group used for classification. Since the aggregation of point descriptors happens over primitives larger than triangles, the labeling performance is improved. Now let's take a look at some statistics and key highlights from this competition. The building challenge took place from March 15 to May 24, providing ample time for participants to showcase their expertise in 3D part segmentation. We received participation from 10 teams, each bringing their unique perspectives and innovative approaches to the challenge. In the building net point evaluation phase, we received a total of 5 valid submissions from the participating teams. These submissions showcase the participants' approaches and algorithms for part segmentations of 3D building models represented as point clouds. And now, the moment we've all been waiting for, the announcement of the winner of the building net challenge for the building net points evaluation phase. It gives me a great pleasure to announce that the winner is Shisheng Shu who secured the first position with a part IOU performance of 31.3%. Xu Cheng's submission demonstrated a slight improvement over the baseline, showcasing his exceptional effort and expertise in 3D part implementation. Now, let's dive deeper into the outstanding performance of our winner. Shichen will present his submitted method and will highlight the improvements he made over the baseline model.
Hi, this is Shichen Xu. I'm presenting my submission to the Building Challenge and my project multi-task suite building understanding with multi-modal pre-training at Stanford CS231N course. I'm currently an engineer at Google and also a SCPG student at Stanford. First, let's talk about my submission to the challenge. I trained a point-next XL model on building at points check for screening building part segmentation. The point-next model improved over point-next plus model in 3 areas: data communication, optimization technique, and model scaling. On the model architecture, it adds an inverse residual MLP layer, which adds a residual connection to the cloud model train deeper, and it uses separable MLP, which adds MLP layers after the reduction stage. This is similar to MobileNet to reduce model size. Lastly, the upper channel of second MLP layer can be expanded for a model scaling. Comparing to the baseline LinkNet, my point-next XL model applied the same random rotation before localization and used the same pixel size 0.01. I used a smaller sample size, 40,000, and applied all the data computation from PointNext. I moved the dataset 12 times for epoch and only trained the model for 100 epoch. For the loss, I used the same weighted cross entropy loss. The test result of my PointNext XL model largely beats MakeNet, but significantly improved over PointNet plus at over 100%. In the project, I explored a new task from building a data set, which is called 3D building type classification. It basically produces a class label for the entire building object, such as castle, cathedral, and church. The chart below shows the class distribution of building types, and we can see it's super imbalanced. I proposed a multi-task model architecture to tackle both doing part segmentation task and doing type classification task. I explored multiple various learning strategies for this problem, including training from scratch, transfer learning from different data sets, multi-modal pre-training using Unity framework, and combine that with multitask learning. Unity is a multi-modal learning framework for text, image, and point cloud. For building text, I generated 64 text prompts, 16 multi-view images and depth map, and pre-process point cloud model for each 3D building to form the triplet trains Unity. I pre-trained PointNext model with Unity from scratch for 100 epochs, and for comparison, I also loaded the baseline LinkNet model and trained it on Unity for 50 epochs. The result on the right shows that a good segmentation backbone can also help train a good Unity classification model. Finally, here is the experiment result on both classification and segmentation tasks. we can see that multi-path learning runs using pre-training consistently achieves top performance on both tasks. You can find more details in this course booklet. And that concludes my presentation. Thank you for listening. If you're interested, the paper will be released on archive. Thank you.
Before we conclude, we would like to thank Shicheng for his presentation and contribution to the BuildingNet Challenge. We would also like to express our sincere appreciation to all the teams who took part in this competition. As we are near the end of our presentation, let's summarize the key aspects of the BuildingNet Challenge. The competition focused on the task of 3D part segmentation of buildings, aiming to advance the state of the art in this field. The BuildingNet dataset that was utilized for the purposes of this challenge provides a rich and diverse collection of building models with annotated exterior parts. We hope that this competition has sparked new ideas and inspired further advancements in 3D part segmentation of complex structures such as buildings. For those interested in delving deeper into the BuildingNet dataset and exploring the challenges and opportunities in 3D part segmentation, we invite you to visit our project and challenge websites. Thank you for your time and active participation. Hi, I am Marius Luisu, and
So we are moving on to the last question.
Just a moment.
So we need to connect. So do you want a USB?
While we set up the laptop, let me introduce the last keynote speaker, Stephen Fox. Stephen Fox is a senior director of robotics research at NVIDIA and also a professor in the Advanced School of Computer Science and Engineering at the University of Washington. His research is in robotics with strong connections to the artificial intelligence, computer vision, and machine learning. And at UW, he also has the UW Robotics and Gate Estimation Lab. And also from 2009 to 2011, he was director of the Intel Research Labs and Theater. Dito obtained his PhD from the University of Bonn, Germany, and he has also published more than 2,000 technical papers and also is the 2,000, no, not quite. 2,000 technical papers and is the co-author of the textbook Forensic Robotics. And he's a fellow of the IEEE and the AAAI, and also he received the Cascade Award at the Major Robotics, AI, and the Software Vision Conference. And he is the editor of the IEEE Transactional Robotics program co-chair of the 2008 AAA Conference of the Artificial Intelligence, and also program chair of the 2013 RSS.
Kai-Chun, can you hear us?
Yes, I can. Yes.
He can. Okay, good.
I think there's some echo.
Yeah, and I can also see the slides.
Maybe you can raise your volume. I don't know. Okay. Kai-Chun, can you say something, please?
Hello? Hello? Can you hear me? Hello?
Yeah, maybe you can just say over.
Wait, should the output go through my laptop?
Do you want to
Hello?
try to unmute yourself?
Are we still audible or us?
But we cannot. Oh, maybe you can turn on your speakers again, because I think.
Okay.
Yes, and maybe you can share your screen.
But even with, yeah, the screen is shared. Does it work?
Yeah, Kai-Chun? Can you
Yeah, I
hear us?
can. Yeah, I can hear you.
Fantastic. Okay,
Oh, we can hear you, so that sounds good.
you can share your screen.
All right, hi everybody. Thanks a lot for inviting me. And I'm going to talk about kind of object reasoning for the concept of forward manipulation, coming more from this, let's say, applied perspective, like what kind of things do we need to model, or what can we get away with for forward manipulation tasks. And it's going to be actually pretty simple, kind of pick and place tasks typically. And also the goal often of the more recent work is actually not to try to do explicit 3D modeling of things, but operate more or less directly on the point clouds of these objects. So here's an example of the more early work we've done, where you say, imagine you have a kitchen and you have a 3D model of that kitchen, right? Which means you even have models of the drawers and doors, and you have a model of how they are articulated, how they move. In that context, what you can do then is, of course, you can have a system. This is observed with a depth camera. And we also have models of the objects in the scene. So what we then do is we do standard kind of object detection. We match these objects against the point clouds and the color data. And then you can do these kind of nicely controlled manipulation tasks, like you can do planning at a high level, like how do you open the doors and drawers. Okay, how you can then see, okay, where do I pick up an object model? Right, and you can do all the higher level planning on top of that. The limitation, of course, of that kind of work is that you assume that you have these 3D models of the objects, which in the real world, in many cases, you do not have. And also, even if you have 3D models of things in the world, then it turns out that going through this bottleneck of 60 pose estimation often results actually in a more brittle system rather than if you would operate directly on the point cloud, because you're kind of abstracting information away. So after this, we moved on and said, okay, let's see, can we manipulate unknown objects? And that means objects for which we have no prior model, or where we're not even aiming at modeling them. So just for context, imagine you have this task where the robot, you can see this is just an external view on the left. On the right side, you can see that's a view from the robot's gripper camera. As a camera that is attached to the gripper. You can see this here on the left picture. And imagine you just want to get that object, like you click on the pixel, or you have a language interface or something like that, pick up the mug. And in order to do this, the robot has to reason about, first of all, what are kind of the objects in the scene, not at a semantic level, but more like, let's say, at the physical level, right? Like a segmentation of the scene into even unknown objects. Then it has to reason about, okay, once I know what the objects are and where they are, I need to be able to reason about how can I pick them up. So what we call graph generation. And then also you want to reason about collisions in the scene, right? Between, for example, the gripper and the object and other objects when you move them around. So the key components for this is really kind of just simple segmentation, graph generation, and collision checking. And we've done a lot of work on training these different components using synthetic data, purely synthetic data. Here's for the scene center generation, for example. You can then, of course, randomize over the scenes, over the background and all these things. And then we had different kind of techniques that we trained on that. It's just a brief summary. I'm not going to go into any details. The most recent one is this object seeker, but many of them are kind of based on contrastive learning ideas, right? Where you say pixels on the same objects should have an embedding that is similar, and otherwise they should be separated. For object seeker, what we did in addition is we also said, if we have multiple scenes and the object appears in multiple scenes, then we want the pixels for that object to be similar in the embedding space, even across different viewpoints and things like that. So that allows you then actually to do kind of object matching and kind of use that to tell the robot which object it should pick up. I'll give you an example for that. Here's just an example what these segmentations then look like. And here again, we're really interested more in the segmentation into objects that the robot can then manipulate. And once we have a segmentation, the next task is, okay, how can we pick up objects? How can we learn to pick up objects? And here the idea is if you have 3D shape models of objects, you can randomly, let's say, try different ways of grasping them, feed that into a physics simulator, and then kind of shake the object and see for which of the randomly generated grasps the object stays nicely in the gripper and for which one it just flies away, let's say. And you can do this, of course, on GPU. You can do this on parallel. We can do this. This is for 9,000 objects from the ShapeNet database. You can then kind of annotate using this rejection sampling technique. You can annotate all these shapes with graphs that have a high chance of succeeding according to the physics simulation. Okay, so you get kind of positive examples for all these different shapes and objects and how you can pick them up. And then we looked at different ways of kind of learning this. This is one technique. It's called contact grasp net, where you can then train that network to take as input a depth image of the cloud, of the point cloud, the scene, and then it generates here what you see on the right side. It generates kind of for the different points that you observe. For each point, it estimates, would that be a good point for the robot to actually interact with its gripper? And also which 3D orientation the gripper should have in order to interact with that point, okay? So it tries to replicate what we've seen from that physics-based data generation. We try to replicate that in the scene, meaning these are the gripper poses that have a high chance of succeeding, okay? And with that, we can then actually, once we have a point cloud, we can then generate graphs that have a good chance of succeeding. The key trick is, of course, that for the data generation, we needed the full 3D object models, but then for the network training, we trained the network on partially occluded point clouds, right? So that's, of course, the key trick here. One other aspect that actually turns out to be relevant is collision checking. Now, you could do collision checking purely kind of point cloud. You have the point cloud of an object, and you have the point cloud of the scene, and then you can do collision checking using voxels or the raw point clouds. The problem is that various aspects of the scene might be occluded. So which means if you just do point cloud comparisons, you're never going to detect those. And rather than going the route of saying, we're training a network to do a completion of the scene, we said, let's just train a network that checks for collisions, right? Where again, the idea is more, we're trying to train components that are driven by these tasks rather than first explicitly modeling the scene. So here's the specific network we had. It's kind of voxelizing the scene in coarse feature voxels. And then we also feed in, for example, the point cloud of an object. And then you can check for an arbitrary transformation. The network is trained to check whether that point cloud of the object is going to cause a collision with the scene if it moves according to that transformation. The nice thing is once the scene is encoded, we can do this very, very fast. So it's actually faster than doing explicit point cloud matching or checking. Okay, and we can do many of those, of course, in parallel. And we can use that also for example, what's called model predictive control, where when you want to try to, for example, figure out how your manipulator can move to a certain position in order, for example, to pick up an object, you need to check for collisions as you're planning the trajectory of the robot. And we can do all of this very, very fast. So now if you go back to that original scene, imagine you say, hey, get me that object, then we can now automatically segment the scene. We can also, for this object, generate grasps using this trained network. And then we use the collision network to figure out which of the grasps are actually reachable without causing collisions with other objects in the scene, right? And then using this technique, first of all, the network figured out that none of the grasps were actually accessible to the robot in that moment. And then here, what you see is the different segments are kind of colored by how much they contribute to these collisions, to desirable grasps. And then we can say, oh, for example, the red one here, that is the one that's contributing most. We can now kind of revert the process and say, okay, now let's make that the target of the robot so that the robot can get that out of the way. Okay, so now the robot figures out a grasp for that object and picks it up because they were not in collision with other objects, gets it out of the way. and go back to the original scene and now go back to the original task. And now it actually can access the mug. So all of this reasoning is done kind of purely, first of all the components are trained purely in simulation, and none of it depends on any kind of object models. It's really operating on the raw point clouds that we might segment, but otherwise it's raw point cloud reasoning. Another thing you can do now, you could also prompt the system. For example, in the upper left corner, you see a picture of the object that the robot should pick up. So here we have the segmentation model that is also matching these images of the target object against the objects in the scene, and then we get the segmentation and we can pick up kind of target objects. The interesting aspect here is that the target objects, they don't have to be from the same scene. They can be just different things, like here the Coke can, for example, is also in a totally different position. And the system is pretty robust for matching those against the scene. So rather than training all these components individually through individual networks, we're currently looking at, we have a work under submission where we're trying to do all of that through a single transformer, right? Where the input to the transformer is the scene point cloud, and the output is, on the one hand side, what are the potential grasps in the scene for the different objects? And also, if the input, for example, could be another point cloud of an object, it's going to say, where could you put that object in the scene? Okay. And we're getting, through the single model, we're getting actually better results than through plugging these individual components together. Here you can see an example on the right side, upper left of these videos, where it's picking it up and it's also reasoning about how it has to rotate the object so that it actually fits into the scene. Here's another one. Again, all of it, this is now just through a single transformer. Another line of work was then, if you can now, you have the scene and you can, let's say, segment out the individual objects, then one question is, for example, can you reason about more complex arrangements rather than just picking up an object and placing it somewhere else? So here we had this work, it's called Structformer, where the idea is, for example, you have the scene and the task is to put the boxes in a row, like you can see here on the right. And the idea here is, again, we're just training a transformer to reason about these individual object point clouds, segments, in order to achieve this task. Okay, so the high level idea is we first have an object selection network where the input is, for example, language message like, okay, rearrange objects that have the same class as the yellow object into a large circle at the bottom right of the table, something like that. And then we take all the point clouds of the individual objects, and the output of the transformer is then first is to select which of the objects the robot should rearrange in order that are relevant for this task. And then we feed that into another transformer down here that then actually generates a sequence of transformations for these individual objects such that the overall arrangement is achieved. Okay, and this is an autoregressive model because each object placement is based on where the previous objects were placed, so that, for example, you can arrange them in a circle, things like that. Okay, and then the training data we generate different. This is also then in simulation where we generate data for kind of different shapes you might generate, like circles or lines, or setting the table, and then also, for example, kind of different kinds of objects, different materials. In this case, it's as you can see, the colors of the objects is actually still pretty simple, but this can clearly be extended to even more realistic objects. This is what the data set looks like. Okay, all these different arrangements you can generate. And then here's an example. Especially the ones, or the lower ones, are the ones we can generate now, for example, where you just say, put them into a medium-sized circle. And then you can see how the yellow objects are kind of being rearranged. Or you can then generate, for example, lines of objects, right? And you can specify, for example, which objects you are talking about. It's not just grabbing all the objects, but you could say all the blue objects or all the objects are the same color as the fork or something like that. Of course, so far, there's no like general language understanding in there. It's really kind of trained on the data set that we can generate here. But it kind of shows, and here's an example on the real robot, kind of that even with this really low level, simple point cloud reasoning, we can already do things that I think a few years ago, people would typically have said you need really more complex task and motion planning. But you can do many of these things, let's say, in a much more planning-free, heuristic kind of way. So far, everything was kind of fully supervised, right? There was always the point cloud segmentation, the grasp poses and things like that. Here in this more recent line of work, we wanted to see, can we do manipulation tasks without actually explicitly reasoning or labeling objects, and focusing much more on kind of the actions that the robot should actually execute. And this, the first line of work was this clipboard. Maybe some of you have seen this, but the idea is it's kind of, it started out with, Andy Zhang did this at Google Transporter Networks, where the idea is that you have a top-down manipulation task, and the input to the network is just a top-down view from a camera, and you specify the task where the gripper should go to pick something up and where it should move to place something. Okay, and that turned out to work actually extremely well, even from very few examples, but there was no generalization. It had to be trained, a single additional network had to be trained for every single task. And then of course, Clip came up. And then what we did with Clipboard is kind of combining these transporter networks with clip embeddings to get more generalization out of it. And how this works, and for example, this would be if you want to train the network to fold cloth or unfold the cloth. Like here in the left, you give it an overhead view, and then you just tell it in this image, like where the gripper should go to pick it up, this red one here, and then later where it should move it and release the object again. Okay, you just give it very few examples, and it turns out that that works pretty well to kind of then generalize to different orientations and things like that. Let me just give an example here of what you can do, like sweep the beans into the blue zone. Just trained from very few examples. Now, if you'd use the kind of techniques that also we saw here this morning already, I think it's going to be much harder to specify these tasks, right? Because if you have just granular media or stuff or things like that, object-specific representations are just not gonna be well suited for this, right? Sometimes it's much easier to specify tasks without actually reasoning about objects. Here's another example, pick up the cherries and put them in the box. And here the network actually learned to pick up the cherries at the stem, because otherwise you would crush them, because the examples just showed that the pick places were all at the stem. Okay, if you would want to do this in a more object-centric way, then you would first have to have your cherry detectors and then the stem detectors and things like that. And just doing this by demonstration is actually a very convenient way for doing that, I think. So far, this was all kind of top-down. Not perfect, yeah, I know. All top-down kind of manipulation. And now in more recent work, we had this core paper last year, Perceiver Actor, but we wanted to do this in full 3D, which means where the gripper poses can be at any 3D position and 3D orientation in the scene. So here the idea is that the input, it's a transformer, and the input is the language, okay, open the middle drawer, like the task the robot should perform, and a voxelized encoding of the 3D scene. The raw encoding is actually at a 1 cubic centimeter resolution, so very fine-grained. And then we generate tokens for the transformer that have a 5 by 5 cubic resolution. And the output of the transformer is then given the language task and the voxel encoding at a 1 centimeter resolution. It's kind of a classifier over the scene that says how likely is it that that would be the gripper pose that the robot has to move to in order to achieve that task. And the output is then also a discretized 3D orientation over the gripper. Okay, so it's a full kind of 60 pose specification. Let me just give you an example for how that then works. So for example, if you, this is when it's trained on, put the tomatoes in the top bin, then the input to the network is on the right side along with that language command. And then the network again generates target gripper poses, a sequence of target gripper poses that the robot should move to in order to achieve that task. So you can see here the first gripper pose. So it's again XYZ and orientation. Then the robot moves to that gripper pose. And once that happens, we call the network again, now with the new scene on the right. The network output says, okay, the gripper should move down and close. And once it does that, it retrieves it up. And then puts it there. Again, during training, it was not trained. There's no object detector or anything like that involved in there, right? It's just trained on the specific example, like with tomatoes and the top bin. So the definition of what the top bin is mostly given by how the gripper should move in order to get the tomato in there. Okay, so what you see here is just some examples of a single perceiver actor transformer, and it's just trained on 53 demos. So there were a few demos regarding like the handstand, where it needs to learn that it has to press the top button. Again, if you do this in an object-centric way, you then have to maybe specify where the then put the lime in the bottom bin, tomatoes in the top bin. Again, all these tasks are trained with a single network from 53 demonstrations, which is in robotics, often we care about not having to do too many demonstrations. But actually where I think this should work, this line of work should kind of move is, rather than training it on 53 demonstrations, which of course doesn't generalize at the compositional level, what happens if you train such a model on 1,000 or 1,000,000 demonstrations, right? Because then you start getting the real benefits of compositional language understanding. All right, one other interesting aspect here was also, if you look at the attention of the network, for example, in this case, the task is turn the right tab, and the attention of the network, if you look on the right side, is on the tab, but it's also putting attention on the top of the faucet. And it turns out the only way to figure out which is the left versus the right tab, you need to look at the context of the whole faucet, right? Because that's how you specify what left and right is. So left and right is not in the coordinate frame, but it's relative to the faucet. And since the faucet can be in any orientation in the scene, the network had to learn that it has to kind of look also at other parts of the faucets in order to detect that. Does that make sense? And the good thing is we didn't have to specify any of this, right? It's just coming through the training data or through these examples. Here's an example now turning the left tab, where it also paid this kind of attention. The problem with this model was, or is that it's computationally pretty complex. So training the perceiver actor on a set of, for example, simulation tasks might take like 2 weeks actually, just because we have these 8,000 voxelized representations for which we always have to generate the tokens, right? And then the transformer is actually pretty fast, but all the token generation, everything. So we now recently developed a new work that's called Robotic View Transformer, RVT, where instead of generating explicitly these 3D voxels of the environment, we are, and it's kind of related what Angela also said, we are actually projecting the scene. We're first generating the scene point cloud and then projecting it into different views into the scene. Okay. And then what we do is we run a single transformer that takes as input these different views. And it reasons about, for each image, for example, what would be a good point where the gripper should go in this image. And then we combine the labels from the different images by intersecting them in 3D. And then we're getting the same results that perceiver actor achieved through the voxelized representation, we get that now through the multi-view representation, but the key advantage is that it's way faster to train. So here's just one example on the training curve, where the dashed line is the one we had with perceiver actor. So this is training over 16 days. And with this new representation, we're getting the same quality of results, the same accuracy, 36 times faster only after 1 day. And we can even, by keep on training, we get even better results. Okay, so just again, rather than explicitly going in this voxel space, doing view-based reasoning helps a lot here. While maintaining, of course, the important aspect, I think, is always that we want to maintain kind of the 3D reasoning. I could give one more, but I think I'm just gonna leave it at that then, right? So that we have time for some discussion. Yeah, I think what we see a lot, especially in some of these simulated environments, that people train robots using RL techniques or evaluate their visual pre-training techniques in kind of just 2D, which means, for example, in the simulated environments, if the camera position between training and testing does not move, then it's very easy for these networks to overfit to kind of a reasoning only in the pixel space, right? So I think it's really important to force these systems to reason about the full 3D scene. And I think after the work I've seen here, of course, I would assume that many of you agree with that, right? And how to reason about the 3D scene, of course, there's different techniques: view-based, voxel-based, nerve-based, and that's totally open. I think what's the most appropriate way for doing that. But I think in general, it's really crucial to do that. We've seen that sim-to-real actually works really well with physics-based simulation nowadays. And this object-level reasoning, there's different ways you can get there, right? One is like what I showed in the first part, explicit reasoning, explicit supervision, but you can also get there, for example, by just giving it this action-based supervision that I showed you with this perceiver actor kind of work. And of course, there's many tasks where that is not going to be enough what I showed you so far, right? If you want to have more fine-grained affordances or reason about more complex things like stuff, things that are highly deformable, liquids, granular media, and all of that, I think then we'll have to think about what is the appropriate representation even for these kind of scenes, especially with respect to how you want to achieve certain manipulation tasks. Yeah, and one question in general is also this kind of notion, this part segmentation, things like that. Should that come out of explicit supervision, or could that just evolve out of kind of in a robotic setting, right? By giving the robot many different tasks, maybe it can just learn to reason about the relevant parts of the objects without you giving the explicit supervision. And with that, I'll thank you.
We have time for one or two quick questions. Yes, okay.
Thank you for this very nice talk. So I like the task, like using language to instruct the robot to do something. So I'm just wondering, like your current framework is always trying to train a unified kind of transformer that things. I mean, on the other hand, since we have all those kind of large language model that so why not go the other way? Say we make use of the existing language model to understand language. We use the existing point cloud net to understand the point cloud. Then we just try to connect them together. Why have to go with this kind of unified?
Yeah, that's a very good point. So on the one hand side, of course, we are using language models for the language tokens, right? And there's a lot of work going on, of course, where people go from language instructions to kind of a next level representation of the scene or of the task for the robot. We did some work. We just had a paper at ICRA where actually it's called proc prompt, where we use GPT to generate for certain tasks. We actually generate Python code.
I see.
Right, we gave it annotations like through prompting. We told it, okay, these are, and we even were able then to tell it these are the skills that your robot can execute. And then it was able actually to generate a list of Python code that then you can call. The focus of this line of work is a bit more on, okay, even when you have solved that, how do you get your robot to actually do these things, right? And that from a robotics perspective is actually the really, really hard part. right? So that's been the focus here. And so even with this language stuff, like what we did with the perceiver actor or so, these can be used very well to instantiate the language models then. So there's still this higher level that has to come on top. But I agree, yeah, there's a good reason to kind of separate those still out a little bit.
Yeah, thank you. Thank you.
Yeah.
So it's probably a beginner question for robotics. So like when you're designing like graphs, trajectory, we usually focus on collision-free graphs with like trajectories, but that for humans, it's very rare that we would not like glide into other objects when we're graphing something. And is that like, do we care about that in practice? And if so, how do you approach that? Or is it like too far away?
Yeah, that's a great point. That and Oski was, yeah, so far still, even our work, we typically focus on avoid collisions. You don't want to, and especially if you want to do work that's also at some point where industry listens to you, they clearly want to avoid collisions. If you get any collisions, they're going to say, no, we're not going to deploy that on our robot. I think one limitation is still that the robots just don't have the sensing capabilities that we humans have, right? We have this touch sensing all over our body, and robots typically don't have that. So detecting collisions and avoiding them is then not so easy once you are in contact with these objects. But I totally agree, of course, that one way to go is people are looking at learning from demonstrations, so that, for example, the robot generates trajectories based on human demonstrations that might look more natural and things like that. We've done some work on object handover where the human has an object and hands it to the robot, and the robot has to figure out how to grasp it and things like that. There you have to reason actually about collisions with the human fingers, right, and all this kind of stuff. So it gets a bit more tricky. But yeah, I agree. I think ultimately I always say, well, like, why are our robots so rigid and stiff, right? Like we should just have a soft skin around the robot so that they can get in touch with things and stuff like that. And there's a whole community out there called soft robotics that actually looks much more at those aspects. Here's one. Yeah.
And thanks for the very nice talk and all these nice robotic applications also around this. I have one question actually. You are arguing very much with the direction of starting at point cloud. But in the results you showed, there are all these artifacts, point cloud sensors, also like depth sensors we have currently, they really suffer with photometrically challenging objects like glasses, cutleries and stuff. So should we forget about the images and start with point clouds and care about these problems separately?
Yeah, that's a good question. So when I say point clouds, I typically actually mean also kind of together with the vision data, right? And some of that is actually using, like, for example, as I said here with this RVT work, that's exactly the idea of actually projecting it into an image plane, right? So that it is more visual-based reasoning. And then in addition to that, for example, this work only depends on you being able to project the scene into these views. And you could then, for example, rather than just accumulating your point clouds, you could run a nerve model to generate those views, right? It might be typically maybe a bit slower, but that's also the direction we are pushing into, so that that you're not operating really necessarily on the raw data, but on something that's already improved on that. So yeah, I agree. It shouldn't be all just pure raw point clouds. Of course, on the other hand, for many of these tasks, the question is, do you train a model to kind of pre-process and denoisify your data and complete your data? Or do you train your more action-driven part of the model to handle that kind of data, right? Like, as I mentioned, you could do object completion and then do collision checking on the completed objects, or you can just train a collision checker that immediately directly works on the raw point cloud.
Thank you so much.
Thank you.
Just a note, we do have a poster session downstairs in exhibition level. If you go down to the NSA, you will find the poster. When you have versus collateral poster.
For it. So when you watch the rest of my minutes, okay?
Yes, so can you people Zoom hear me?
Yes, I can.
Okay, great. So, I am thank you for being here today. I am not going to chat with our principals, right? And then I will. I really do to get benefits back and forth around. And then we very well. So you know, around or the he's not a form of my We will have in Colorado. While we are working on the middle school into building the particular for your population. The giving of your and in the culture
Very well. Already the video with the little training with the work from the 16. It work from the temporary he was qualified by the people for this and we the people. And he will be people involved data that can complex and on properly development. We get reasons to the home robotic. Otherwise, there is and I don't think it's a CVPR with the data results, but I still want to upgrade us and to share some necessary things. Overall, it will be fine. When they investigate this very minus funding control. Some of the share projects including state and private regulation. For the Second, we propose to which how we can then understand given instructions and given the choose of classes. And then we give you an example of the user input I explained on the table, how we use the and the using a different model to and then it's really to something thing, so it's going to find Spanish and then bring it back to the user. So it's very complicated path and requires language understanding and also understanding the surrounding environment as well as their own capabilities. So here I have a Spanish and the user will use it to apply. Here we can already play this. Thank you for this. And you're just signing so we do so in this case, if a language model as per my brain can should be built so fire on the language that we do only the brain and language that I'm sorry I didn't just say it. The problem is that language models are thinking that the way that is not longer in the environment, not there in the state, or capabilities. However, maybe it's self-analysis and creating the to be joined in business. Where the language is not safe. So we need to rather than fully understanding their capabilities. So one area that we can very capability and performance is to use robotic performances. So here's the video of the environment performances. They essentially kind of free with the final policy was learning. It will provide another contrast, and another contrast can be seen as a proxy for performances. And when you like in this video, so you can see we have the shows that we were that's really that is what this so we can also same understanding or stronger same understanding. Right, so then in the same power, we basically have two branches. One branch is the free power branch, where it will store your stats that are equivalent to our components. For example, the top is probably the table, everything that is related to the Apple state. And the ruling in this everything on that don't want to do with the high scale. And then when it is and then repeat this stuff until the entire task is spent. So this is actually how they have it. But it's all useful in general. So can we do a little bit about it? I want to do it on one line. First, I think we remember. Yes. And there was on 16 different writers. So that's freedom. All of the other hand, is space that was done to the chunk. That is the point that we can write off. That's better than the so was a new so it means you can store this right. So and then we will just that's where you use the longer you but you have to on as say here we right there. So means style and we use right things and whenever see the here so we're here to measure something in which means it has a sound opportunities something that you can see. So every year will smart the scale and so this makes it happen longer assembly using so in this case when the number is here and it's not so that is not but only see I see so it's like I see it and so they try to definitely so far we have found we can do it conservation. But we do see we spread the team first and then we get some runs and the parts. We're not going to it's one of the it can be and do some sort of so we have different names such as the Google can be this so signals and the difference here is that we instead of we want to fix the number of first we will generate option and then the set of the treatment to find the treatment of the address. So we give you an example. So we figure out the spread of let me read the signal presentation that is grounded by the file. So basically, we have XYZ, we have P10 and And then we have other like language, such as and then we're a PQ from where I'm doing and theory. So in all theory, which is important, it was 200 regions. So it often contains some foreigners, so to speak. And I'm thinking I will compare one of them. But that could be so these two concepts are very good. However, because they have not really explored on the same, you have lawyers and obligations and lawyers with and then you're procedures to make that up. Taking arrangements and basket. They'll read into your every hour. Every time. This is really good to design or a different these papers. Thank you so much.
So let's move to the last part of this workshop, which is the poster presentation. I'm sorry. It's like it much faster than what I was expecting. Okay.
It had no if your to the same point says
individually.
Which will operate articulate operate rather due to the massive prior knowledge of the efficiency are likely to be successful. In this case, we try to decide interaction modes. The aim to build representation characteristics at the moment which from the very for instance, this table is central as a joints, which I want to flag the most. The kind of flag the most study, the kind of the same serial census or the categories. Some other system is solely inspired by the information with personal saving the computation interaction based and a number of points relating to the interaction from the sponsor and the foundation observations the illustrated can be distinguished and conquered using purposes to next, we show steps attention strategy. We also preserve the channel during the life. It's a number of 7 cells. The treatment construction is not a certain part of the mission. Constructed cells on all categories, especially for small parts. The solid shaped parts in the main space can successfully resize the other parts. Similar results can be observed using random parts from a certain shape category to those new shapes. After the interrelation shapes of these transitions within the corresponding parts of the pair. Thanks for watching.
I was like fast. So it's that first. Unfortunately, there seems to be an issue with this speaker and it doesn't have any sound. Last year, we student and PhD for the laboratory and assessing lab by sharing our latest research work to chat with the engineering and knowledge from reading by class, making our lecture and agriculture, young and background in Compositional. Reconstruction of using the presentation of problems from service contract to spiritual design flows. Many languages like personalization and complex grammar solutions to task and task have limitations such as inconvenience, inaccurate, or lack of methodology. Our approach involves particularly by planning the clusters using connection networks, using services to these clusters using analytical and techniques, and refining the model that is using various methods and assumptions. We integrate on services with people's requirements into a changing real space, which involves explain translation of sentences for high fidelity thinking and student extrapolation. We evaluated our code with various Python's application styles and verifying a cap offers commands performance in several measures of popular literacy dataset. Examining and gathering that closely reconstructs the practical from segmentation and ultimately involves indicators and used words for models. So one component is called by our poster, which is project code for directing them, sets up structural feature, make a correct Again, short ends with dynamic difference in curves in 3D shapes. 3D representation of CVPRs for 3D scans is a concept development. However, we really difficult task due to the unstructured nature of 3D scans. The limits of the connect is to return to the targets during the 3D scan. Most of the stated article failed to return the parametric regions on most scanning. On the region corresponds. The 3D EF data set. Automatic inference of parametric challenges from 3D scans. End-to-end code consisting of 3 modules in the value of decomposition. Consistent code using the rapid sampling to sample points near areas of high patterns. Then the extract point features using the point also encoding. The decomposition module is used to back out to report points with their desired process. The parameters of measurements. Results should the same to recover evidence by most 3D models, sampling scans as recognized details. Quantitative results show that the two results on 63D and PSE and 86 set. And the conclusion, sample plan is an end-to-end memory that is able to be with parametric and population of shown evidence from its 3D scan. We have one last.
We introduced 3D SSR, 3D subscene retrieval. As the complexity of 3D scenes continues to grow, we observe that it is important to be able to retrieve subscenes of interest. In a 3D SSR pipeline, the user specifies an anchor object and a set of context objects using axis-aligned bounding boxes. And we see the mesh corresponding to these boxes to the right. For a 3D scene in the database, we assume that the objects are equipped with axis-aligned bounding boxes, but categories are not provided. To tackle 3D SSR, we first compute the intrinsic similarity using object codes derived from a training encoder. Next, we measure the extrinsic similarity between a 3D query subscene and a potential target subscene by computing the geometric overlap between them in the world coordinates. To compute intrinsic similarity, we have developed our self-supervised encoder, which outperforms prior work for the task of 3D subscene retrieval. On the left, we see a 3D query subscene, and we observe that our retrieved results at ranks 2 and 3 are most similar to the query in terms of geometry and object arrangements. In the next example, we observe that the alternative model that uses a self-supervised encoder does not provide any matches at ranks 1, 2, or 3, but our model is able to provide powerful matches at all ranks. Thank you, and please join this poster session if you have more questions.
Thank you so much. Okay. Thanks everybody for staying until now. That was the last poster presentation, both here and in Zoom. Thanks again, Kaiju, for doing all the hard work in terms of preparing the workshop. And yeah, if you are here in Vancouver, join the poster session. Bye.